Exclamation point. Okay, YouTube has started. Number 3, nice. Oh, you just passed up Joseph. Okay, let's get into the Discord. This is the final reading group session for this E&M, so it's a hype day. Especially got two of yours. Yeah. So I think today we're gonna focus on waves because that's something that Cook said would be like the important thing to look at. I'm doing good. How about you, Eldridge? It's rainy here, and I enjoy the rain. Okay, so let's put in our first problem here. My bed, looking to the black screen, and there you go. It's always an enjoyable time. Cozy as always, hell yeah. Dude, like, I was just thinking about that this morning, like, why is it so cozy just being warm in bed? Like, it's so, when it's cold out, it's just so hard to get out of bed when I can just stay in bed and be warm. So number 7 here says, consider the two oppositely traveling electric field waves. I'm just convincing myself that these two functions are indeed traveling opposite. You know, I feel like I need to see the identity here. Oh god. What's my undo? That's my undo. Oh? $10?
Hey, Don.
Hey. How's it going?
Doing good. How you doing?
Doing good too. Excited for the last session here.
Yeah, traveling waves, huh?
Mm-hmm. Okay. Yeah, so I think Cook said like waves would be a good thing to focus on for the last like session here, so this is the first one that I saw that had waves. Oh, thanks, Eldritch. Yeah. With the pen spinning. Yeah, the link is in the usual spot.
And, oh, yeah, right? I always forget. Let me grab that. Let me get on that.
No worries.
I click this little open chat, and then I'm here.
Right. All right, thanks for the work, Eldritch. Okay, and then I guess I haven't looked at what part A says yet, but I guess they do E1 plus E2, and they use some kind of trig identity to combine them. That's what it seems like.
Now I'm trusting you have your trig identities memorized.
It's always the pluses or minuses that get me on these.
These ones I learned these in high school, and so I didn't forget them. You know, a lot of things I learned in high school I still got in my head.
I wish I could say the same.
Kind of like I was young enough for my brain still to properly absorb things.
Yeah, maybe.
Cosine
Okay.
A minus
This is
B is cosine A cosine B.
yeah, the cosines come first, right? That's what I was trying to remember. Cosine
Yeah, the
kz,
cosines come first,
cosine.
and then it's going to be a plus.
Oh, yeah. Omega z, close those parentheses. And then this lower me the same thing, but with a minus in the
With the
middle.
negative.
Okay.
Yeah. And a couple of your T's turned into Z's, I think.
Uh, why did yeah? Why did I do that? um, why? Yeah. Oh, it's KZ. Oh, I okay, yeah. That's because I was rearranging E1 and then I forgot I unrearranged it. So wait, KZ omega T, KZ omega T. Okay, so it's these Z's that are bad. T T. Okay. And then I need to change that to a minus. And then the signs cancel, and that's how we get the formula they get. Okay. Okay, well, we can at least understand the setup of the question then. That's a good start. Hey, Bibs. Find the magnetic field associated with the standing electric wave by finding the B field associated with each of the above traveling E fields, then adding them. So I'm looking back at the okay, yeah, it is E equals plus or minus C. Well, that's the constant. Can be perpendicular to each other and also to the direction of propagation. Now, I want to say that example that they were doing, the electric field went along the z-axis and the B field went along the x-axis. Like the x hat. Oh, sorry, that's both the waves are going along the y-axis, but E pointed in the z direction, B pointed in the x direction. Do we know the direction of propagation?
I think we can work it out by what's in the parentheses, maybe. If it's kz minus omega t, then as t varies, then z has to vary. So I think it's going along the z-axis.
That makes sense, yeah. In their examples, they had y's in the parentheses and it went along the y. Okay. So then if it's going along z, we should expect B to have y hat.
Oh, okay. So now, if they got a typo in the question, then I'm confused because for part B, I was just looking at part B and it says it's got exactly the same thing you just came up with. Unless I'm reading it wrong. Maybe that's just supposed to be a y hat and a, I don't know. We'll get there when we get there, I guess.
Yeah, I am not sure about that yet. I assume it's going to involve curl or something somewhere.
Hmm.
Okay, so do they need to be the same function otherwise? I think they do. Like I think we only change the magnitude because E naught equals plus or minus C B naught, and then we change the unit vector. But I think like the cosines stay the same.
Yeah.
So E or B1 should be E1, but just slightly different. So we're saying this is Y hat B naught cosine KZ minus omega T. And then B2 is the same thing, but with a plus. And then we would add these together and get our standing B field, I guess. Which it should look the exact same.
Yeah.
Okay, so we don't. Let's not go back through all those trig identities, I guess.
No.
To C Y hat B naught cosine KZ cosine omega T.
Unless, I mean, when it says E naught is plus or minus C times B naught, how do we know if we take the positive or the negative?
I was wondering about that too.
Um,
I'm honestly not quite sure.
Well, wait a second now. I want to say it depends which direction the wave's propagating. Yeah, on page 441, they say something about that. Just
Yeah.
before section 9.5, there's like section 3, the bullet point 3 or whatever, and it says, oh, so it depends if V is positive C or negative C.
I don't know how to work that out.
I'm trying to remember how you do that. So it's something to do with the argument of the trig function, right? So we've
I
got
guess so.
cosine, and inside the parentheses, we got kz minus omega t. So yeah, let's think about it. So what happens is if t increases a little bit, then you're making that argument smaller. So you'd have to make z increase as well, wouldn't you, to make the kz part bigger? Does that make sense what I'm saying there? I'm actually just looking at the
Sort of.
I'm looking at
yeah.
Yeah, I'm looking at what you got for B1 here. So, oops. So right here we got KZ minus omega T, right? So basically what you do is you set it to a constant. Like you set the thing inside the parentheses to a constant, because if we keep that constant, wait, is that how it works?
I'm sort of we want to keep the same V or Z value and look what happens like with T's. But like
I guess,
I
yeah,
don't know how
you
you
could do
define
that
forward or
too.
back.
You think of it, let's see. Yeah, if the argument was constant, right? If you set kz minus omega t to be a constant,
Okay.
kz minus omega t equal to constant, right?
Right.
Then what that means is the cosine of that of that argument would be constant. And what that means is that our amplitude of the point on the wave would be constant, right? So what that means is you're looking at a specific height of the wave and keeping the height constant. So then if t, I don't know if it makes sense what I'm saying. So I'm thinking if you let t increase, then because of the negative sign, you'd have to have z increase as well, right? They'd have to both go together to keep it constant. So as time's moving forwards, the z coordinate of that sort of height of the wave is moving forwards as well. So I think that means it's going in a positive z. I think that means the wave's moving in a positive z direction.
And the other one we're doing the opposite. I think I see what you're saying. We're like, you're tracking like one little point on the cosine curve, or not a point, but like a height.
Exactly. Yeah, that's what I was trying to say. Good. I'm glad you understood what I meant. Yep.
And then you're tracking whether that's moving like in this 2D thing, like right or left as time goes on, and it must be moving right. Okay.
Yeah.
That first one. Okay. Yeah.
So the B1 magnetic field, is that what that is? B1's the magnetic field. That would be moving to the right, and the B2 is moving left.
Right. Or I guess like positive Z and negative Z. I'm
going to erase this because it might be in the way.
We don't need to change the I like we don't need to change the cosine to a sine or something weird like that, right?
I don't think so.
Yeah, I don't really actually like starting with just an electric field and figuring out what the magnetic field is.
So the E1 and the E2 they give us had those same signs, right? Like the E1 had a negative and the E2 had a positive.
Yeah, I guess they should be the same. Like it should be the same function otherwise.
Because I think so. So I want to say the E1's moving right and the E2's moving left.
Yeah.
And so if the E1's moving right, the B1 should also be moving right, shouldn't it? So that seems fine. So I think everything you did is good. I think it all checks out. At least it seems to make sense to me.
Okay. Well then,
I don't know. I'm noticing it's a 2-star problem, which makes me a little nervous. Oh, that's right. Standing wave. So it's going to have nodes, isn't it?
Yeah.
Use Maxwell's equations to find a B field. Oh, I get it. No, I understand part B now. I was reading it wrong. To find the B field associated with the standing electric wave, which is what that's why I was confused. I thought they were talking about that being the standing magnetic wave, but it's not. Sorry, my bad.
No, I'm still not quite clear how we actually do that. Like, we could use the formula curl B equals mu naught epsilon naught dE dt. That's, I think, on Paris law, just the displacement current term. We'd have to integrate it though. And we looked at the integrated form, I think, in both the last two sessions. I want to say we did at least.
Yeah, we did. I still don't have it right in my head though.
I think it's like a line. You undo the curl using a line integral. Okay, yeah. I'll rewrite it here.
Okay, thanks. Yeah, because I don't think they didn't put it in the summary at the end of the chapter, I don't think.
No, I mean they only ever provided like one of the problems we looked at. It wasn't even part of the chapter. So you integrate.
It's always nice to cheat off a problem by using another problem against it. I like
Yeah.
that.
uh, so a line integral on b equals mu naught I, which is going to be 0, plus mu naught epsilon naught. Surface integral d dt dot dA. Oops, partial. Um, what are
So if
we?
it's so,
Yeah,
the current zero, isn't it? In
yeah.
this case, we'll have to. Okay.
The first term will be 0. Do that. I don't quite know what we will be integrating around though, or through for the surface integral.
Yeah. Oops.
I feel like there's gonna be some easier way.
What if we just tried to use the other version where it's the curl one? Is that
Uh,
helpful?
I mean, we definitely can get curl B. That like we for that it'd be curl B equals mu naught J, which is still 0, plus mu naught epsilon naught dE dt. Hey Phobos, thank you, thank you. I still need to go back and fix. I think it was like day 4, whatever one I couldn't like quite do, but maybe I'll do that after this. Hope you're doing well.
Yeah, nice going yesterday. I didn't see the programming, but well done.
Yeah, there's some fun problems in that Advent of Code site. We told on 5A last night. I didn't even look at 5B.
How's it work? They put up a problem every single day.
Yeah, a problem each day, and each day has 2 parts. So I guess it's really two problems, but it's kind of like they build on each other. Hey Zumedo. Oops. And hey Give. To learn them, we're using this book here, and we've just learned about Maxwell's equations. Oh yeah, absolutely, Phobos. I'd love to get you in for one of these. So
Phobos versus Dawn versus Zach, like a triple header.
yeah, I feel like Phobos has like I would put my money on Phobos there, but it'll still be fun. So yeah, Zumedo, we're trying to figure out how to use Maxwell equations. Like we're given um, a standing electric wave, and we're trying to find the B field for it. And
Actually, you know what?
yeah,
Couldn't we just oh, it's the same problem, isn't it? We're trying to uncurl the curl.
yeah.
Well, if we take the derivative with respect to time of E,
Mm-hmm.
we're going to get a what are we going to get? We're going to get a cosine of z times the sine of t, aren't we?
Right.
But the
That's
sine
not
of
good.
t, don't you treat the sine of t kind of as a constant in the curl? Because the curl's just dealing with position, isn't it? Not time.
Uh, maybe.
Yeah, maybe. I know.
And we just look at what the EDT looks like. So it seems like it's going to be helpful here regardless.
Yeah.
Um,
Let's like soldier on here and try and because if you've got a curl of a vector field and it's only a z, it's only in the z direction, then what does that mean? I don't know what that means.
me neither.
I've been trying to review a little vector calculus, but it's just going slowly. I'm still doing some line integrals and yeah.
Yeah, the more I do this, the more I want to read that DivCrad curl book.
Yeah.
Um,
Well, I read most of it, so I guess I'm a counter example to the fact that it always works. Yeah.
well, counterexamples are helpful in proofs. So we get a minus and we get an omega out front, sine omega t. Is there a book you mentioned before that was linear algebra and vector calculus? Ooh, I don't remember it. If there was.
That book was the book I'm thinking of. I think it's called Div Grad Curl,
And all that. Yeah.
or it might be called Grad Div Curl and all that, something like that. And it was nice because it was. Oh yeah, Don's gonna pull it up. It's just very concise too. It's only of maybe 150 pages.
Yeah, I kind of like how short it is. Like,
And they're small pages too. I mean, you can sort of burn through it. But I
oh,
really like
good.
the way he
Okay.
explained he explained it kind of like a physicist, like kind of like they do in this Purcell Morin book.
Okay. I don't mind that.
Yeah, I don't mind it. I think it's good if you can. I don't know. It's almost like my brain's trying to see it from a math perspective and a physics perspective, and they're at war still right now. So I got to see they have to come together peacefully so I can understand it.
I like the intuition of physics. I feel like I need to build the intuition before I can understand the proof, usually. Um,
So now, could we just say like let B equal bx, by, bz, right? So we're sort of going to hypothesize this B field in space, bxi plus byj plus bzk, and then we could take its curl and set it equal. And wouldn't we have enough information, like three equations, three unknowns or something to find the three components? I think maybe it works.
um, I think like yeah, because we could also get more information because we know the divergence of B is 0. So that might be something.
Oh, okay.
Or like that might be another equation if we need it. Um,
Oh, I see. Yeah. Because I guess in the general case, you do need more than just this one equation, don't you? But I think in our case, it's simple enough that we might get away with just this equation.
And I guess we do know it's only b. Ooh, is it only by? Yeah, there's only a y component.
Oh,
Curvilinear coordinates. Curl. Oh wait, let me set the start here. I guess we're doing it Cartesian. Oh, okay. So we only expect a y component. So I think we could boil down to just the middle term. What I'm seeing in the back of the book. I mean, it might be helpful to have the other terms equal to 0, though.
yeah. I want to just do the whole thing.
Okay. So then del cross b
I'm going to
is.
put in the I hat, J hat, K hat here.
Oh yeah. So D B Z Dragon Ball Z over dy. That's
Oh,
gonna
we
be
should
a lot
set
of
up
letters.
the determinant. That'd be
Oh
nice, wouldn't it?
yeah.
Yeah. Let's.
So I don't have to just copy down.
Sorry, I'm terrible. I just sit here and watch, and I backseat drive the whole time.
No, that'll be easier than just like flipping back and forth. To be honest. Okay, so it's del cross b, so del goes first.
Yeah.
Uh, After this critical in like 2 hours or something, I can take a look. Okay, so the first one is d dy d dz by bz.
So you finish up the physics reading group, and you got some physics waiting for you. That's great.
Yeah. I remember critical even asked a question like using Coulomb's law to find the field of like a rod of finite length, and was actually able to do it. So that was nice.
Yeah.
K hat. Okay.
Now that I look at it, maybe
This
instead of
isn't.
IJK, I should have used XYZ, right? Because they used in the book, it looks like they're using XYZ
Oh
for the
yeah.
unit vectors. Well, anyway, we could set I equal to X later.
Yeah. Maybe I'll just do a plus and then reverse the order here. dbx dz minus dbz dx. No, zoom it. I use a tablet to write with. Just make sure I reverse that right. Yeah, I think that's good.
Yeah, that Wacom tablet's paying off.
Yeah, it's really nice. It's one. It isn't even like Wacom brand. It's like it's called Huion, but it was slightly cheaper, and the reviews seem to say it was about the same. So
Nice.
yeah. Okay. Um. Oh, you know what? We actually curl B. We only have an X component, don't we?
Yeah, so we have to set that first. So what do we do? Set the first parentheses to what we had for the curl, and
Yeah.
set the other two parentheses to 0, maybe? Oh God, this is
Um.
much worse than I thought it was going to be. Sorry, I thought this.
I mean,
For
I
some
don't know
reason, I
what
didn't
else
think
to
that.
do besides this. So, ugh. Equal to
Hmm.
minus 2 omega E naught cosine kz sine omega t.
Maybe the other two things being set to 0 is going to help a lot.
0. And so we actually want to, or the thing we actually want to solve for is each of these B components.
Yeah.
Um, and I think in theory we should only only this d by dz term should be non-zero. That's what I would think.
Yeah.
For anything
That
involving
sounds right.
by. Well, yeah. uh, okay, maybe I should actually just write these separately. dy minus d by dz equals that dbx dz minus dbz dx equals 0. And then that thing over there is also 0. So I think that's 3 equations with 3 unknowns.
Yeah, just they're all kinds of
The
they're all tied up
operators.
in the partial
Yeah.
derivatives. Yeah. So if we know bxz is bzx and bxy is byx, I'm thinking this means bxz equals bzx, bxy equals byx. How does that help?
Hmm. Well, it's annoying because it doesn't match any of the other combinations we have up there.
Yeah.
Huh. Um, well, if we can, without trying to do it with math, if we can justify that the same way we did in part A, that B should be propagating along the y-axis and only have a z vector component. If we could just live in the world where we have this portion of the equation and everything else is 0, we could integrate that with z and get something that's really similar to what we got in
Yeah.
part A, but it's going to have science instead. Which I don't know how to deal with that part.
Yeah, that's true. It's going to have signs. Well, that doesn't feel good.
But yeah, I don't quite know what else to do with this thing, to be honest. Like I almost feel more confident that this is right than what we did in part A now. Cosine is going to integrate to positive sine. We have to divide out a k. So that's another bad thing, isn't it? So maybe this isn't quite right. I don't know if we want a plus c or not. Or maybe there's some crazy way that our answers still match, but you have to use like the co-function trig identities to turn a sine into cosine or whatever.
So we've got K and omega
Right.
as kind of like parameters in our functions.
And we would want them to be equal to C if we want to match part A, ignoring the difference in trig functions.
That's what I'm just wondering. Like, how are they related to C? Do they even have to be? I mean, the question didn't say these were light waves, did it? It just said oppositely traveling electric field waves.
Aren't electric field waves also light waves?
Well, I don't know if they have to be. What if I just had a magnet in my hand and I, started moving it? Wouldn't that make... Oh, you're saying the electric field waves that generated by that motion travel at the speed of light regardless of what I do, right?
Yeah.
Oh,
That's what I think.
yeah. Okay, so, well then we should be able to find some little equation relating K and omega and C, I think. I used to know how to do this.
I mean, that's what I'm looking for right now. I'm thinking that, like, back to the original definitions of E that they gave us, if you were to factor out the K, I'm just like back up by the original problem right now.
Okay.
Equals x hat E naught cosine K parentheses Z minus omega over K T. Is omega over K basically our velocity because it's being multiplied by time?
Okay. So we might be able to use that later. Yeah, because that omega over K, isn't that in the place where the V was showing up?
Yeah, yeah.
Yeah, okay.
So that seems possible to justify that we could turn omega over K into C, I guess.
Yeah.
Then the only thing we have to resolve is do we want cosine or sine?
So that's where the E naught C showed up, right? The B becomes E naught times C.
Yes. We might have needed to also change something else.
Okay, what about this? Let's see. Okay, is there a trig identity that'll get us back? So sine A times sine B. Can we write it in terms of cosine A times cosine B? How did that work again?
I mean, if we use the same trig identity rearranged, sure. Yeah, go for it.
Yeah, you got it. Yeah, cos A plus minus B. Yep, good. That's just what I was going to do.
Oops, wrong B. So, yeah, I mean, like, the sine part, I guess. But we'd have to hope for, like, we're not going to get the cancellation that I think we want. And hey, Stooky. Looks like there's another vector calculus and linear algebra book. I don't remember ever hearing about that one. It was like it would fit the bill, though.
Hubbard and Hubbard.
Mm, this is
So do you think
annoying.
part A was wrong somehow? I don't know.
I just gotta feel good about what we did in part B. It's probably a faster way, but I I don't know. In the example, okay, well, we're looking at a standing wave. I should look at an example of a standing wave. I think that's better. So many fields don't exist. It's all a cover up. Hey, weren't you?
Oh,
No, the standing wave, it does have the same trig functions. But then their final answer. Wait. No, these are not standing waves. The first two things, they add them together to get the standing wave, and those have the opposite trig functions. But they aren't ever given just the E field. Standing waves are just lazy. It's better than a sitting wave, I guess. Huh. You saw one at the beach. So, okay, I see in the last sentence of the example here, in contrast with a traveling wave, the standing wave has its electric and magnetic fields out of step in both space and time. Like, one is zero when the other is at a maximum or a minimum. And that's why I feel like we should expect our answer to have sine rather than cosine.
oh, so maybe we're not wrong. Well, but we still have different
In part
answers for
B,
part A and part
yeah.
B.
I think part A is wrong. I can't quite justify
Okay.
why, though. We should have less time to stand. They have time to clean. True. Finding the B fields associated, and so I can only imagine. Well, hmm. The C in front shouldn't change anything. I feel like we did both of these right. Obviously we can't have. Uh, this is the text here, orange hue. Do you want to change your mind? I guess so. Oh, I think I meant to wait. E equals plus or minus c b naught. I think I need to divide the c rather than multiply it in part A. Yeah. But
Oh,
I think it's making it even farther apart from our answer for part B though. Because the omega over k I think agreed with what we just had, but I'm noticing in the example that E
yeah.
is what it is, but then over in B they have E naught over C.
Yeah,
Oh
I was
wait,
looking at that just now too. So maybe change those to E naught over C.
yeah, I guess so. Actually, so maybe the way I had it, I don't know if it was fine or not. Doesn't matter. This is so weird.
There must be something wrong in part A. I mean, when I look at this example, they're doing the sum of the electric fields and they're getting a sum of sines.
I think for one of these equations we need the minus in our B equations. That will get us the signs when we apply the trig identity. I think one of these in the E naught equals plus or minus C B naught. If it's traveling, whatever wave is traveling to the left, I think needs the minus, and that was the second wave.
Okay. Yeah, that's what I was looking at earlier. I mentioned that, but yeah, there's something going on with that, right? I think there is.
Yeah, and that's gonna make us get the other cancellation from the work we did above it. Well,
Yeah, so it won't be quite so simple.
uh,
I
I
mean, it's
mean, we
still
just get the
easy,
sine instead
sure.
of the
Yeah,
cosines, yeah.
yeah. It's just that it wasn't really just like cutting and pasting what we did for the electric field.
Oh, yeah, it's not as simple as that. Okay, well, it's good to know. I guess that does matter. The plus or minus. Okay. And then I'm gonna say when we add them, we just get the sine terms and they are positive. Okay. And we need to
Yeah, E naught over C instead of C times
yeah.
B naught.
But then
Now, what about this C?
yeah, we want omega over k to be 1 over c, but I said it was just c to match part B. I mean, what must the units be? K has to be inverse meter because it's being multiplied by Z.
Inverse meters, yeah.
And T or in omega is inverse time.
Yep. Yeah, so we get meters per second. I mean, that checks out.
We're saying that B is equal to. I didn't copy something down wrong, right? It's an omega. Or what is it? The omega out front came from the partial with respect to t of the function they gave us. So that's okay. Do we actually divide by C? Not. Yeah, I think we do. That's such a weird issue.
I know it is. I don't see. I'm looking at it. I don't see it where it's wrong. That's why I feel like we've gotten it mostly right. I'm getting willing to just look in the back of the book now. I think it should be E naught over C, but I can't see where we should flip something or. Is it something to do with an epsilon naught versus a mu naught? Because I know C pops up as some kind of ratio between those things.
Right. We just don't have any epsilon naughts or mu naughts to work with. That's what I. Where did they go? Oh no, I dropped them. That's why.
Were there supposed to be somewhere? Where were they?
I have to multiply mu naught epsilon naught times dE dt. Because
Oh, damn it! There it is. There it is. Okay.
yeah. Mu naught epsilon naught. Yeah. Okay, that should fix it because it's equal to like 1 over root, or it's 1 over c squared or something.
Something like that. Yeah.
Okay.
One over C. Is it 1 over C? I think it is 1 over C squared. Wait a second. Let's see. They have it here. Yeah. Mu naught epsilon naught is 1 over c squared. Yep.
And that will be perfect. Okay. We don't need that cosine identity anymore. Okay, so then b is equal to 1 over c squared for the 2 out front. Omega over k is just c. E naught y hat sine k z sine omega t. I don't want to put the y hat there, but okay. 2y hat e naught over c sine. Okay, perfect. I think we got it right then. Ugh.
We had mistakes in both parts and we found them. Good. Nice.
Yeah. Nice call. I'm glad you thought about that. All right. Well, I guess let's see how, like, I want to see what the right way to do that one was, because I assume we did it the
Sure.
wrong way. That was number 7.
Don't we always? That's fine.
It's true. Ahmed, thank you for the follow.
If Ren was here, he'd tell us how to do it, how we did it wrong.
Yeah. And I would thank him.
Yeah.
Plus or minus y hat directions. Okay, so we did correctly put a minus sign on B2. Okay. Oh, do they do the same thing? Wait, del cross E. Oh, they do the other. Okay. That might have been. Oh, that is easier. Del cross E equals minus dB dt. That's the differential form of Ampere's law, I think. Huh.
So instead of uncurling B, we just should have curled E. Right?
Yeah.
Oh, good grief. You know what? That kind of makes sense because I sort of think of the electric field and the magnetic field. It's kind of like when you're doing a second order differential equation for like a spring a mass oscillating on a spring, right? And if there's no damping, you get a perfect sine wave because the second derivative is like the negative of the original function, and the first derivative gives you like the velocity, right? So the E and the B kind of feel that way a little bit, like in some sense the derivative of E is the B, and then the derivative of B is the E again. You know, so like the second derivative, you get back to you've gone around to where you started from. I know it's not a perfect analogy because all these things are like three-dimensional now, and there's other things going on, but
that makes
it's
sense.
So much easier. Yeah, it's so much easier to differentiate instead of trying to go backwards like we did. But oh well, yeah, we got there.
Yeah, and ours is what Cook was saying with a changing E field causes a B field, and a changing B field causes an E field.
Yeah. Isn't that weird? It's like the chicken and the egg.
Oh, wait. Well, alternatively, you can find BV, the Maxwell equation, del cross B equals the thing that we did. And you should check this gave the same result. So we were just working ahead.
Oh, okay.
Okay. Nice.
Yeah, nice. Mu naught E naught is 1 on C squared. There we go.
Okay, this one, it doesn't seem like all that relevant, but it's a 1 star, so let's it'll hopefully be a confidence builder. It just seems like a calculation. RMS. I remember them talking about it. I forget how you get the RMS though. RMS magnetic field strength.
Oh, RMS stands for root mean square.
Right.
So how does that work? If you just had like a bunch of numbers, you would square them all, take the average, and take the square root. So in some sense, that's kind of like how you find the variance, isn't it, in statistics? It's like you
Oh,
square everything first to get to, so you don't have to worry about things canceling when you add them up. You kind of
right.
square everything to get rid of the negatives, then you take the average, and then you take the square root to get rid of your squaring. Root mean squared.
Yeah. And they give us the power density in sunlight is roughly 1 kilowatt per meter squared.
Okay. Yeah, maybe on page 447, I saw you looking at it.
Oh, 447? Okay. I didn't see the actual words root means square, so I moved on. It might be that E bar thing.
Yeah, I think isn't that what they did here to get these things?
There's some sort of averaging happening. Um,
Oh, okay. E bar squared is the mean square electric field strength.
uh,
So if we just took the square root of that, we'd get RMS, I think.
that tracks. Okay. Um, okay. RMSE, root mean square error, is also a common metric used in machine learning to quantify how good are the model predictions. Oh, nice, playing Alice. Okay. I mean, yeah, if we can just use that, then I guess we're given what S is. Um, 1 kilowatt per square meter. Hey, okie dokie. Welcome in. You not epsilon not. But we expect S to be in watts per square meter. So that's 1,000.
I think that's mu naught over epsilon naught in that radical.
Really? Oh, there's a slash in there. Ah,
Yeah, they hit a slash in there.
thank you. Okay. Quick math-related question if you have time. Yeah, that's quick. We can take a little look at it. Okay. And then Wolfram, 1,000 watts per meter squared times square root. What is mu not called again? I'll see if Wolfram will do this.
Is it called permittivity of
That's
free
epsilon
space?
naught.
Oh, that's epsilon naught. Is it permeability?
Oh, it might be.
Totally guessing. Is
It is.
it?
Yeah. I assume there's some semantic difference between the words there. Maybe that's what they talk about in, like the next few chapters.
Yeah, because it comes up with, I think that's the one that comes up with capacitors, like something to do with how easy it is to set up an electric field in space or
Yeah,
magnet
and
or
like
electric or magnetic field.
dielectrics and stuff.
Yeah, dielectrics, exactly.
Kg squared meter squared second to the sixth ampere squared.
Well, we wanted to take the square root of this, didn't we?
Yeah.
So what would that give us? Kilograms meters
I
over
guess I can put a square root on the
amperes
entire thing.
seconds. Yeah, it looks good.
Yeah.
Because amperes per
Electric field strength level just does it for us.
newtons per coulomb. Yeah, I think that gives us newtons per coulomb.
Okay.
Yeah, good.
6 Oh wow, do we have to worry about? No, they're not gonna talk about significant figures, right? I'm going to say it's 613.8.
Now wait, we're not done because we're looking for RMS magnetic field strength.
Oh, nice catch. Um,
Well, isn't that just like scaling it by C or something? Oh, no, there's more than that, isn't there?
um, I
Or
don't.
isn't there? Maybe there's
Ooh,
not.
I imagine it's just C.
Okay.
I guess you want to divide by C. Yeah, let's just try it. Oh, and I see your question there. Okie dokie. Oh, it does give you Teslas.
Really? It just gave you Tesla?
Yeah.
Man, this Wolfram Alpha stuff is pretty smart.
Yeah. That's not vector B, that's B bar. It's pretty tiny, which I guess that makes sense. 2.05 times 10 to the minus 6. I guess Teslas are big though.
Yeah.
Okay, let's make sure this one is right, and then we'll. It looks like Okie Dokie's question is quick, so
Cool.
do that quick. 614. Okay, yeah, they do the approximate 377 for root mu naught over epsilon naught, but that's fine. 2 we don't times
Oh,
10 to the minus 6
we did more
Tesla.
work than they did.
Yeah, we were more exact. Okay, yeah, we got it right.
0.02 Gauss, 1/20th of the Earth's magnetic field. Oh,
That's actually kind of a lot.
yeah, it is, isn't it? Just from the sun, just shining on us. Wow.
Yeah.
It was a nice sunny day here, even though there's like 3 feet of snow.
Oh, it's sunny with the snow still from like yesterday.
Yeah, it's pretty. It's all white. It's
Oh
nice when it's
wow.
all white. It's cold though. It's 27 right now.
Oh God. What is it? I'm probably in the high 50s for me. 54. Okay, so okie dokie, you have an object that's 0.66 inches by 14.01 inches by 9.77 inches. And you have a space that is 11.25 by 15.5 by 1.25. Oops. Okay. It looks like the answer is yes, because I just when I think about it, I kind of like pair up the smallest measurements with the smallest measurements. And as long as your space is, as long as each, in the space that you have, as long as each of these numbers are bigger than like their paired number, you're okay as far as like can think of. So, I would pair like the 0.66 inches of whatever you have is smaller than the 1.25. The next biggest 9.77 is smaller than the 11.25. And then 14.01 is smaller than 15. So you're probably okay. How close is the fit? Uh, Pretty close. So, I mean, you only have an inch of wiggle space for the two blue ones, and then maybe an inch and a half for the two green ones. Actually, well, no, the two red ones are the closest. That's just half an inch. So if they're kind of odd shapes, you might run into an issue if you get more than half an inch of like bulge or whatever for the red measurements. So it seems pretty close, I guess. Okie dokie indeed. He also asks, you're not the biggest fan of how you go about making it fun. It kind of depends on the person. I like math when I can see why it's helpful. So trying to use math to, even for like a simple task like this, just like, I think makes it more fun. In general, I didn't enjoy math until I took a calculus class though. So unfortunately, a lot of math you kind of learn before that to me just isn't that interesting and only somewhat helpful. So I don't have really the best response, to be honest. I'm sorry. I don't. Do you have a better idea for that part from books?
I mean, I like math because I like puzzles, and so I feel like math is fun when it feels like a puzzle to me, but a lot of people don't like puzzles. So if you don't like puzzles, then that's not going to help looking at it that way. Like when I saw this problem, I'm thinking of it as a little box trying to fit inside a big box, you know? And
Yeah.
then I thought about, I think I thought about it the same way Don did, maybe like rotate it in your mind in 3 dimensions or something, right? So you can, the length and width and height, you want to try and get the, yeah, get the biggest one with the biggest one and so on.
Yeah.
But
So
how do you make it fun in general? I don't know. Try and turn it into a, try and turn your math problem into something that's more interesting to you, I guess.
yeah, you like it because there's only one correct answer.
Now, see, that's what I like about math. Math's the only
Yeah.
thing in the world that math's the only thing in the world where you actually know if you're right or wrong. Everything else is like we don't know.
It's all gray area. Yeah.
Everything else is philosophy and politics and stuff, and it's like, oh no, I don't save me from all that.
Yeah. Um. Yeah.
Although, let's face it, philosophy and politics are interesting, but math is the nice thing about math is that it's not gray like that. You know, it's black and white.
Yeah.
Most of the time, it's black and white.
It's like difficult, but you can always like see the path ahead, and that's not true for a lot of other things. Um. And okie dokie, if you do ever find yourself like with another like random math question or something, there I'm not the only one out there, so there's a whole list of people there who all like do math help in some form. Yeah, thank you for the question. Okay, it's the next one I have pulled. Oh, okay, here's a pointing vector one. It's probably good to get a pointing one.
Hmm.
Um, Oops. Oh, I just flipped it. Oh,
What'd you
wow.
flip?
The formulas. I didn't know you could do that so easily.
How did you do that?
I'm just dragging the corner to make it smaller, but I brought the bottom corner up above it by accident. So thank you for the follow,
That's
okie dokie.
that's actually kind of cool to know. I mean, for text, it's not so nice, but if you had a graph, it'd be nice to be able to sometimes
Oh
flip it
yeah,
that way.
yeah.
Hmm.
Okay, so consider standing wave in equation 9.32, which I dragged down here. Draw plots of the energy density, script u, y of t. I probably should have grabbed that formula. See, oh, I could have deleted those, but not important. Wait, this is the equation that we want, right? They do give a slightly different one down below. Oh, sorry, u is not the pointing vector. S is the pointing vector. Wait, is that what we want? What's the question? No, we do want u though. Okay, there's a lot of different versions of u. Well, what we're given E and B. So, okay, maybe we want this equation. Right here. Sure thing, critical. Is there... I think that's fine. There's a couple of versions of U here, but I think they all mean basically the same thing. Okay. And we're going to just integrate with respect to time after. -1 over, well, I guess we should do this cross product separately. And I guess we want x hat, y hat, z hat. 0, 0. I'm just gonna put a dot 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 there for E. I'm going to write that entire thing, and then B only has an X component. Okay. We only get one non-zero determinant here, right? And that's from the middle one.
Nice.
The E dot 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 and the B dot 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 times y hat. Okay. And I guess now I'll stop being lazy and I'll actually write out each of these. So we're just gonna multiply these two things together. And yeah, we remove the unit vectors. So we're gonna get, there's a minus sign out front, and there's a minus sign in B, so those cancel. 4 E naught squared over C. Sine 2 pi y over lambda, cosine 2 pi y over lambda. That came out terrible. Cosine 2 pi ct over lambda, sine 2 pi ct over lambda. Do we have a nice trick I need to clean these up?
Yeah. 2 sine cosine is sine 2 theta. So that
Right.
4 in front, you can split that into two 2s and use 2 double angles.
And so inside we're gonna get 4s?
Yeah.
Okay. Oh. Okay. That seems simple enough for E cross B. Now we need to take the divergence of that. Whoa. Oh, I dropped my y hat.
Y hat, yeah.
So that just means we only have the y component, so we're just going to take the partial respect to y for our divergence.
Yeah. Okay.
Oh, good. We don't have to do a product rule.
Nice.
4 pi e naught squared c lambda cosine 4 pi y over lambda sine 4 pi c t over lambda and no longer y hat. Okay. And then that means the integral of du dt dt is going to be minus 1 over mu naught. Don't forget that.
Yeah, I had my eye on that this time.
Okay.
I did.
And then this thing that we just got. Oop, not that. I don't know if it's my tablet or a scowl drop, but it sometimes has a little bit of lag and messes up when I'm writing.
Yeah, I noticed that too. It seems more to happen more when we get more on the page. Like it started complaining to me a little
Yeah,
bit.
it did do that to me too. Okay, so we're integrating the sign here. So it's going to introduce a negative, which will cancel the negative in front.
Oh, the 4 pi over lambda cancels.
Yeah, you're right.
And we get a c squared on the bottom.
C squared on the bottom right. The mu naught, yeah, that stays. So we have E naught squared, C squared, mu naught.
Yeah. Because the negative cancels too, right?
Right. Now it's cosine. No, not dt. Okay. So that is a fancy U. And we have to plug in omega t values.
Hey, look, they told you in the problem U should be a function of y and t. Oh, maybe that was, I don't know, maybe that should have been obvious, but sure enough it is. A function of y and t.
Yeah.
That's good.
The energy sloshes back and forth between the different energy plots. It's a funny word to use. So omega t, I assume 4 pi c over lambda is equal to omega. Like that bit there. Because we don't have an actual omega anywhere here. I think it's just the coefficient of t.
What did we get for that previous question? Didn't we have lambda and we had k instead of?
We had KZ and
omega
omega
over
t.
K.
Um,
Omega C and lambda, how are they related? I didn't scroll too fast. I'm closing everything. Where was that?
I mean, I want to say that omega is usually. I mean, does what is lambda here? Like, can we verify this thing as inverse time dimensions? They use lambda somewhere in this problem.
Lambda is usually the wavelength, isn't it?
Yeah. And so we have c divided by lambda.
Divided by lambda,
So,
right? So
inverse time.
omega, I think. Yeah.
I think I think the entire thing is omega besides t, like 4 pi c over lambda. I think.
I would keep the 4 pi out of it.
Really?
I think
Okay.
so, yeah. But I might be wrong.
If we do plug in 4 pi, our example points become 0 pi, 2 pi, 3 pi. Oh wait, no, there's pi squared in here.
Oh, I see. I don't like pi squared. Let's do what you said.
Okay. Yeah, I don't think we have a good way of knowing whether it's supposed to be besides that.
I know.
And so it's really, I guess it's just gonna be controlling our amplitude because we still have a function with respect to y. Zero, pi over 4, pi over 2, 3 pi over 4. Is this better done in Desmos? I feel like it's probably better. Yeah, I kind of want to put all these at the same time in Desmos. I don't imagine there's a great value in drawing these by hand.
Okay, yeah. Sounds good.
Well, what do we do with all the other constants?
Oh, wait a second. Draw plots of the energy density at omega t values of this. Oh.
Yeah, I
So
don't.
each one of them is gonna be a cosine wave, isn't it?
Yeah.
Yeah, I think I see what's going on. So it's a standing wave and it's some kind of energy density. So as time varies,
I don't know what we do with all the other constants. Maybe just let them be one?
still kind of confused by the omega t. So you're saying the omega t will be 4 pi c over lambda, right? That's what we should try.
Yeah.
Or that's omega. Omega is 4 pi c over lambda.
Mm-hmm. So ugh. It seems weird to just let everything else be one, but what else do we do?
Well, so what that's going to do is it's going to turn our second cosine into a constant, right? But the first cosine will still be a function. So the whole thing will still be a function of y. So Okay, cool. I like this. I'm seeing your Desmos there.
Okay. Or oh
Yeah, because everything else is just sort of an amplitude factor, right?
yeah. So we start with amplitude one, and Lonesome Cowboy, thank you for the follow. The cosine wave decreases a bit. Pi over 4, it flattens out at pi over 2. And then from flattening out, it goes up a little bit and then comes all the way back out to 1. Are
Yeah, it
these
makes
zeros at the
sense. It
same
makes
point?
sense. It,
Okay.
it
Yeah,
makes
they
sense.
are.
It looks like a standing wave moving, right?
Yeah, it does.
Yeah.
Is that expected? It does have the form of a standing wave, I think.
I think they said it was yeah, the
Oh,
title of the
yeah.
question is
Okay.
yeah.
um, Maybe I'll paste a screenshot into the scale draw. Okay. Now what does part B ask?
The energy sloshes back and forth between the different energy plots. Hmm.
So the pointing vector is E cross B over mu naught. And we already know what E cross B is. And so we're doing omega, I guess the middle omega t values. Oh wait, I need to divide out the mu naught. But that's not going to really matter. If we let everything in from B1. It's really the same thing but with signs for the purposes of this graph here. Sine pi over 4. Oop. Ugh. Pi over 2. Is it 3 pi over 4? Okay, then swing by these plots are consistent with how the energy sloshes back and forth between the different energy plots. So maybe we want to look at just the same omega t value. And so when really, so for pi over 4, the blue is our energy density and the red is our pointing vector. And this just feels like a derivative. When the energy density, and I guess it is because energy density involves the pointing vector is the derivative, more or less.
Can you leave those two graphs turned on, but turn on the third one as well for cos
Uh,
pi over 2?
yeah.
Because I just
Also,
want to see what that's.
for the sine one, also pi over 2.
No,
Okay.
just the cosine one. Oh, that's the one that goes to 0, isn't it?
Mm-hmm.
Oh. Hmm. So the red one's supposed to be the pointing vector, right?
Right. And so I'm just saying, how like when the blue is at a peak, the pointing vector is at 0, and when blue is Well, actually, there's a negative sign. When blue is decreasing the fastest, the red is at a positive peak. But they do kind of chop off the negative sign in the definition. Oh, God. And then when cosine is entirely flattened out, or when the energy density is flattened out, the Poynting vector is at its maximum. And then one more omega t later, we get the reverse situation of the first one.
What is this pointing vector doing?
Um,
I thought it showed the direction the energy was moving.
and it is, I think.
The power density, flow of energy per time per area. I'm just reading that from the text.
Yeah, I just saw the same
S
sentence.
gives. Yeah, okay. Energy can't disappear. If the energy in a region decreases, it must be the case that it flowed out of that region into another one. I didn't see in the Desmos pictures how that was working.
Yeah, this is a standing wave, so... Huh.
Do you think we got a mistake in part A? Because when we plugged in pi over 2, the whole thing turns into 0, right?
Yeah, but it seemed like it was happening in, like, it's part of the transition from going, like, as part of the progression going from cosine, from going like omega t equals 0 to pi over 4, it's decreasing. And then it flattens out
Yeah.
at pi over 2, and then it goes negative. So it feels like part of the transition, I guess, to me.
Yeah. But if you got energy density 0 everywhere at that time, then like, where's the energy?
Yeah, I don't know. I imagine it's transitioning from the electric field to the magnetic field and back again.
Hmm.
But I feel like the question is implying that it's going between script U and S, which doesn't quite make sense to me. So S is the flow of energy per time per area. Now, how about U? U is the energy density of an electromagnetic field. And S is the power density. So energy density versus power density. No, I don't get how energy would transfer between those two things. I definitely get how they could transfer between electric and magnetic, but I don't know if that's what they're saying.
We got a negative sign missing somewhere. I think I'm thinking of the standing wave a little bit wrong, because I'm thinking of two kids with the jump rope, like going up and down, and there's nodes in the middle.
Mm-hmm.
But the standing wave, the electromagnetic standing wave has like the energy field might be doing that. Sorry, the electric field might be doing that, like in the YZ plane, but the magnetic field's doing it in the XZ plane or XY plane or whatever. But I think they're out of phase with each other, aren't they? Because I was thinking of nodes as being where everything's zero, but that can't be. It has to be like when the electric field's zero, the magnetic field's maximal, and vice versa.
Mm-hmm.
So how does that show up when we try and graph this in Desmos? I guess we're just taking the energy density over everything, aren't we? I mean, this is not in the X or direction or Y direction. This is like the whole.
Yeah, I don't quite get how to interpret like the difference in the formulas too, because like in the formula for you, we had to take the divergence of the curl and then integrate with time, but then the pointing vector is just that one curl value, and it feels like we should be able to just like compare them this directly, but it seems like they do have some type of relationship here.
Yeah. Yeah, you're right. The pointing vector is E cross B over mu naught. Whereas we kind of took the divergence of that to get the divergence of it, and then we integrated with respect to time. Oh, my Calc 3 lets me down again.
Yeah, like the divergence of the curl feels like something special. Like I feel like we were talking about that in an earlier chapter. I don't remember though. Hmm. Famished, I'm not spoiling a thing about the Fallout show. Once you finish it, we can talk all about it. But if you're still watching it, I don't want to spoil it. Pray you just keep watching. E cross B. That's the direction of propagation of this wave.
Yeah, I think so. And the wave's carrying energy as it propagates, right? So that pointing vector tells us the direction the energy is moving.
So if E cross B is 0, that means that one of the E or B fields must be 0 because they're perpendicular, like even if they weren't.
Yeah.
Um, and so we don't actually do it. They don't tell us to plug in something where it does give us 0 though, which is kind of funny. But it should be at 0 and pi.
Actually, here's something strange. If you set up, if you form a standing wave by superimposing two kind of equal and opposite, what am I? Two equal waves that are going in opposite directions, right? Isn't that how we set it up in the first place?
Mm-hmm.
Yeah, so they're exactly the same wave, but one's moving right with velocity c and one's moving left with velocity c. Then doesn't it seem like their sum should basically kind of be doing nothing? Like if the one's carrying energy right and the other one's carrying the same amount of energy left at the same rate, it feels like if you added them together, then they shouldn't be moving energy anywhere at all.
Um,
I mean, it feels that way.
I think that's why one is sine and one is cosine. Should I need to unmute? Thank you, Lonesome. There should be some cool demonstration of this. Maybe. But like that's something I've been trying to figure out. Like, how does a standing wave transfer energy? If because it feels like it's not moving. Um, where is that one website we're using for circuits and like electrostatics? That's what I'm trying to find right now. Okay, here.
Uh-oh. Come on, Excalibur.
Oh no. Yeah.
Yeah, it's doing its thing.
Okay.
Maybe that's why, I mean, when we went around like one full from 0 to pi or whatever, we got half the time the energy was positive and the other half the time it was negative. So maybe just on average, it's kind of not. Yeah, kind of like if you had a mass on a spring that was just oscillating, and in the long run, it wouldn't really be moving energy in any direction. It would just be like kind of like it says, sloshing back and forth or whatever.
Oh, I guess so, yeah.
But I don't know how the Poynting vector works with the signs. I didn't get it. Because what I wanted the pointing. I thought the Poynting vector, because you know how it's pointing and it's like, well, you know, it's funny because it's the word pointing. I thought it pointed in the direction that the energy was moving at that specific instant. But when we graphed it, it felt like it. Actually, wait, can we look at that graph again on Desmos that you had up? Maybe it was right. Maybe it did make sense.
I mean,
Because
we can definitely draw a relationship between these.
because when you had the the energy at the peak, was the pointing vector 0 at that point, at that instant?
Yeah. So red is U, purple is pointing. They definitely have this kind of like give and take relationship. Like, I wonder if we added these up, we'd probably always get 1. Or maybe -1. Can we do that?
Oh, that one on this.
Oh,
So the
yeah, well,
pointing vector is 0 everywhere right there?
right, at time 0. So the energy being transferred is at its highest or lowest, depending on where you are. Well, that phrasing might not be good, but they kind of
Wonder
like,
why in the
yeah, they transition together. Go on.
in the question they specifically like avoided the 0 and the pi, but I wonder why for the pointing vector part.
Yeah, I don't quite get that myself. If I take the pointing and U and add them together and have a parameter for time, oops, I need to show it. Oh, never mind. That's not what I thought it would be. I don't know. Do you want to look at the answer and see if they explain it?
Yeah, I feel like we didn't get this one maybe all the way right, but
Yeah, I think we did. I feel like we did the calculations right. It's just I don't really know the interpretation.
yeah. All right.
I guess before I go, let me get a screenshot in the Excalibur. Copy, paste. Okay. And this was number 9.
9.
Hey, Milk. Yeah, so like we know that a standing wave is 2 traveling waves. I guess we're kind of confused on overall how a standing wave transfers energy if it's just standing there. I guess that's what I'm confused on.
Minding its own business.
Yeah. So they have us plot the energy density and the pointing vector for the same standing wave and explain why it's consistent with how the energy sloshes back and forth. And that's kind of is that explained part that we've been stuck on.
It kind of reminds me of in a circuit where you have a capacitor and an inductor and no resistors. And I think if you set it up right, it's what they call a tank. But for some reason, like the energy can just oscillate back and forth between the capacitor and the inductor.
Okay.
You know, if there was no losses at all.
That makes sense.
And that's what they say in that case. Like the energy goes from being electrical energy in the electric field inside the capacitor, and then the current flows back through the inductor, and then when the capacitor is uncharged, like all the energy is in the inductor in a magnetic field. This kind of feels like that a little bit.
Yeah.
But I didn't quite understand how the graphs were getting us that.
Okay, they just throw out all the constants that were given in the problem and make their own? Okay. Uh, why do they have sine squared, cosine squared? Wait, is there a simpler formula that I missed?
We got the product of cosines, didn't we? But oh,
Or what did we have? Yeah, two cosines. You're right.
maybe we did have the wrong U. I don't know. It looks like the same U. Energy density.
Where did they say this formula? Should I look in the chapter summary?
That formula might have been in the summary at the end of the chapter, maybe.
I don't see the U anywhere in the chapter summary. I'm gonna be annoyed if they're using a formula that we weren't given.
It looks familiar. I think we did know. Oh, you know what? Maybe Don, maybe it's from chapter 8. Maybe that's where I saw it. Maybe.
I didn't quickly see any script use in the power part of chapter 8. Actually, let's just look in the chapter summary.
No, you're right. I don't see it there either, but I recognize those formulas from somewhere. Maybe they were earlier in chapter 9. Energy transport. That's weird. They look very familiar. I don't know where I saw those before.
Yeah, I don't see it. Is did like could we write what we have as sine squared cosine squared plus cosine squared sine squared?
Maybe. But I think our graph is just different. They had the graph I saw there, they had something that never was going negative, I think.
I mean, I don't. What are they plotting? U versus KY? Energy density cannot be negative.
Yeah.
Okay, so we were wrong.
If they've just got a sum of squares of, it couldn't be negative, could it?
Yeah, okay, we were way off, but I don't get why what we did apparently doesn't work. This formula does, like, I agree that it does seem familiar. I don't know where they talked about it though.
They got energy density of an electric field in chapter 1. Epsilon naught E squared over 2.
Oh. No, and then they take the one from chapter 6 and add them together.
Was it chapter 6, the other one? Probably.
Or maybe it's chapter 7? I don't see it. Energy stored in magnetic field. It's more or less b squared over 2 mu naught. There's an integral in there, but I don't know if that's important for that. Oh yeah, the integral goes away because we're talking about density. This should also work though. Why doesn't it work?
I don't know, but it sure didn't, did it? I mean, we got negatives coming out of it. I was not happy when I saw that whole thing go to 0. I'm like, where'd the energy go?
E cross B. If you dot it with del. Yeah, you just do the derivative with respect to y.
You know, that equation 941.
Yeah, it's one that I thought we should use.
Oh. Okay, I found it in chapter 9. It's actually on page 448. It's just it's not given a number. It's sort of in the paragraph about the pointing vector.
Oh. Ugh.
Right before they, yeah, right on page 448, right under pointing vector. It says energy
Yeah.
density of electromagnetic field, which we label U, is given by this. I still don't know why what you did didn't work. I don't know. Was there something wrong with my double angle formula? 2 sine cosine is sine 2 theta, right? That's sine 2 theta is 2 times sine theta times cos theta.
I think there's actually, when I did the cross product, we have a negative sign, like I'm looking at the 2x2 determinant that I got, the only non-zero one. There's a negative sign from the cross product. There was a negative sign from B, but there's a third negative sign from the determinant of the 2x2. I don't think that's the entire problem, but I did drop that.
No, that just throws a negative in there. Yeah, I was looking there earlier when I was wondering if we missed a negative.
Yeah, that definitely doesn't do everything for us.
Hmm.
It using it might be possible that we are. No, it can't be. We can't be right because the graphs don't match. I was just wondering if we use the double angle formulas for cosine, if you get something that looks, because those involve cosine squared and sine squared, you would get closer to something that looks like what we have. But that's gonna be a lot of like foiling, and I don't want to do that. Ugh. I just gonna so. What is the answer saying beyond this? 5 given times the cosine squared and sine squared are either 0, a half, or 1. The energy sloshes back and forth between regions where ky is close to odd multiples of pi over 2 and regions where it is close to even
Yeah,
multiples
I
of
mean
pi over
that
2.
that makes a lot more sense.
Hmm.
Makes a lot more sense. It almost makes me wonder if the formula we tried to use was just not, it wasn't valid for our question, but I don't know why it wouldn't be.
They specifically said in the paragraph before that it's valid for all waves, whereas the example they did before was only
Yeah,
for traveling. So,
yeah, I know.
oh, let's see how does their pointing vector? How far off? That looks closer to what we have. Sine 2ky cosine 2 omega t. I mean, I don't want to make all their constants, but this, if I insert the minus sign that I dropped from part A, it looks pretty similar. There's sine of something y, and oh no, that's sine and cosine. Yeah, no, they have two signs, one with y, one with t.
So our pointing vector was right then.
It looks pretty similar. Like maybe there's some constants that it's off by, but
What is that capital A they're talking about in the answer?
it's some constant. They made it a equals e squared, or a equals 2e naught.
Oh,
And we do have an e naught squared.
and a 4 as well, right? We had a 4 at one point.
I can't read my writing down there. C squared. Oh, I took E cross B. It's a C mu naught.
Yeah, that's a mu naught, isn't it?
And so they do have an epsilon naught and a C in the numerator, so there's probably a mu naught. Well, that's even more annoying. Why is our pointing vector right, but the how is that possible?
We did something wrong with the vector calculus we were trying to do, I think.
I guess so.
I don't see it. I just don't see it. Is there something wrong with that divergence step? That's a step I keep looking at, the divergence.
Hmm.
Hmm.
I might have missed canceling this. No, I didn't miss that. Oh wait, well, when I take the, this shouldn't have a minus sign, because we, no, it should, it should. I don't know. Maybe if I give Wolfram Alpha, if I make ky equal to y and omega t equal to x, I wonder if Wolfram Alpha gets something that looks similar. I know it can't be the same, but I wonder if we're like just off by a constant term that would have just been like a vertical translation up, and that would have saved us or something. Cosine squared y, sine squared t.
Oh, wait, we're doing an integral. We need a plus c, don't we? Maybe that's what you're. Maybe you're right. Maybe it's the same thing if you add the right constant.
Maybe, yeah. Huh. So Wolfram Alpha does say that the answer the book gets could be written as like one half times parentheses 1 minus cosine 2x cosine 2y, which we do have the cosine 2x cosine 2y part.
Yeah, I think maybe we were okay. We just had to. I think we had to put a plus c in there and try and work out like what the average,
Yeah.
like shift it up by the average energy, right? Or something like that. And the answers in the back, did they show more than one
Yeah, they have all
wave, like a
five.
different, and was it
Um,
kind of like what ours did? Like it went from one thing to a flat line down to the upside down wave?
so omega t equals 0. It seems like it's only mins or maxes, and I think we had a transition step, but omega t equals 0, we're at a maximum. Where's it? There. Um, where if we do 1 minus what we have, I think we match. This would match. So how do you? Okay,
Yeah,
there.
look, it's doing what ours did. It's just flipping over and going through a zero, but we just had to find that average value. That's all it does.
Yeah. Okay. So I mean, the minus
So
sign did also mess it up, but that and the constant of integration, I think we are okay. But we shouldn't have gone down through it in the first place if we had solved that one formula. Um. Hmm.
yeah, once again we found a harder way to do it, but this time it bit us.
Yeah. Ugh. I know that's not the most satisfying. Like answer to this, but I guess we weren't that far off at least. It was just we chose the wrong formula. I mean, we should still figure out the
Well,
interpretation piece, or to figure that out a little more. I'm sorry, what?
I think even the formula was okay. It's just we needed to think of it. We needed to
Use the
think of
formula
that
better.
constant, the constant of it, constant of integration, you know, U
Yeah.
plus C.
Thank you, Raven. Energy sources. Bounds of integration. I'm not sure what to make the bounds there. I I assume we had to figure out some type of a initial condition based off the physics of it, but I don't know what it would be immediately.
An initial condition.
Yeah.
Yeah, we just had to think of probably the way to think of it would be to think of the whole thing being electric or the whole thing being magnetic. But then if we thought of that, we probably would have thought of the other form of the U.
Yeah. What did it say about part B? These points show energy flows from one picture to the next in figure 12.127. So they only do the middle ones, I guess, to show the transition. Pi over 4. So maybe pi over 4 shows the transition from 0 to pi over 2 is what they're showing. Right at pi, the pointing vector is 0. And right at pi, the wave goes from minimum to baseline to maximum. That doesn't make sense. Points to the left of this y value have a positive s sub y. That is a rightward flow of energy. Points to the right have a negative s sub y. Energy flows into the region around ky equals pi. Huh. That's interesting. Energy is flowing, and at pi, it does reach a maximum after. Pi over 2, there is no energy flow anywhere. Wait, is pi over 2 another 0?
Yeah, pi over 2 and 3 pi over 2. I
But
think.
pi was a 0 and it had energy flowing.
Say that again.
Well,
Pi was a
yeah, they use pi as an example where to the left there's positive and to the right there's negative, so energy is flowing in. But then they go to, are they talking about a different time for pi over 2? Pi over 2, they should have energy flowing out, not just no energy flow. Oh, no, I'm interpreting omega t equals pi over 2 is a different thing. Okay. Never mind. Yeah, pi over 2, that makes sense. There's no energy flowing, but why is something still changing?
Well,
I don't know.
in some regards, it wouldn't have felt right if we didn't get our butt kicked by the last final problem in
That's
Purcell
true.
and Morin.
Yeah.
Feels pretty apropos of the whole book.
Very fitting, yeah. Ugh.
Yeah, Purcell and Morin, they had to get one more smack at us on the way out.
Yeah. Yeah, I guess there's still Cook's final that I'm gonna want to do at some point. But
he sent the final. Oh, that's right. On Discord, he sent the final to me.
yeah,
All right.
so that'll be cool.
Yeah.
Um, but yeah, I guess we can call the group here. I don't feel that confident in the answer to this question, but I feel like I have to read it a bunch more times to get it.
Yeah, I'm happy to take a loss on this one.
Okay. And Raven, yeah, I'll
Well,
switch into questions in a second.
yeah,
So,
thanks a lot for doing this. So it was a long. So when did we start? When did you start this?
I
I
see
want to
I
say it's
pinned a
been
message in
several
May.
months. Was it May?
So yeah, we're around like I think in late May is when we started. So more than 6 months,
Close to
about there.
close to 8 months.
Yeah. Oh yeah, you're right.
Or,
We'll say
or
it.
is it
Yeah.
7 months? Yeah. Over 6 months anyway. Yeah, I was thinking about it this morning. This might be like the longest class I ever did.
Yeah. I didn't really have a plan for how long it would last, but like I don't think I thought we would get all the way through to Maxwell's equations. At some point I thought I'd get too hard. But
Well,
thankfully
you kept
not.
us going. I mean, if it was me, I think I would have bailed a lot earlier. So I appreciate your tenacity. You kept me on the path to stick with it.
This kept me on it too.
Here's
I don't feel as much motivation without the Saturday like deadline coming up every time. But all right.
Well, it's been fun. Thank you.
Yeah, thank you so much for being here for these. These sessions have been awesome. So
Hopefully, we've learned a little bit. I feel like the big thing I took away from this was learning that electricity and magnetism had any applications to like relativity. I mean, that was the thing that blew my mind the
yeah,
most.
that's
I
still
think
my
that was
favorite
the
part of
newest.
this.
Yeah, I think that was the newest thing for me. I felt like how could I have sort of looked at physics so much as I have and not ever realized that?
Well,
It's not like I was ever a physics major, but I did enough physics courses that I would think somebody would have told me that at some point, and I would have like had my ears open enough to be surprised by it. But no,
did you ever do
I
a
didn't
class
realize
on
it.
relativity?
No, I never took a class
Oh,
on
okay.
relativity. No,
Maybe
nope.
that's
I'm
why
kind of
then.
glad I'm glad I didn't. If I did, I probably would have bombed it. Stuff is confusing.
I'd much rather learn it through Twitch than through an actual class. At least for how my physics classes went in college.
Yeah, yeah. Twitch is nice, isn't it? It's just like very relaxed.
Yeah, low pressure. All
Well, anyway,
right.
next enjoy your next Saturday and enjoy your next Saturday.
Yeah, it'll just be
I'll
normal
be
math
thinking about
streams
this.
for a bit at least. So, all right.
All right, I'm checking out. Yep.
Yeah. See ya.
See you, Don.
Okay. All right. So that was the last reading group session. Um, until we start up a new one at some point. So yeah, Raven, feel free to put your question out there. I'm gonna need a minute to switch my title and category and stuff. Okay, Twitch is updated. Need to update YouTube. No, critical. I'm still I'm doing math. what is the domain? Log base 2. Oh, that's a funny question. Critical did ask if they could ask a question first. But if Critical's question is a lot longer, I might try and do yours quickly. Because I don't think that question will take too long. But I'm still updating my stream stuff, so not that. Okay. YouTube info updated. Get rid of a bunch of those. Oh, did I? Please tell me I downloaded the image. I think I did. I did. Okay. Come back here. Ooh, you got a Kirchhoff's rule question, Critical. Okay. It's gonna take me a minute to remember how the hell to use Kirchhoff's rule. If you don't mind, let me do Raven's question, because I think it's not gonna be too long. And then I'll come to yours. No formula can't apply to this problem. I mean, I might not be able to either. I'm not that strong on Kirchhoff's. Yeah, 10 bucks. So I'll probably need help with it. I'll paste it in below here. But I'm going to work on Ravens first, because I think that that'll be a quicker one. Find the loop direction. Oh, usually you can choose any loop direction you want normally. You just have to be careful with the signs. So Raven is a function log base 2 of log base 3 of log base 4 of x. And so the only thing to watch out for with log is if you just have a normal situation, log base 10, let's say, of x, we have to assure that x is greater than 0. It has to be a positive number. And the base isn't important. So the same rule applies to base 2, base 3, base 4, all those bases. So from the inside, we know that x needs to be greater than 0. But that's not the end of the story, because the graph of just log base 4 looks something like this. And so right here, like there's a negative portion of the graph and a part where it's 0. And so when it comes time to do the log base 3 of this, we need to make sure we're not plugging in 0 or negative into the log base 3. So really, we want to find the x value that gives us the positive portion of the graph when we like go out one layer of parentheses. So any log is 0 at 1. And I know that because if I say that log base 4 of x is equal to y, is equal to 0, I can put this back into exponential form, because base 4 means the base of the exponent is 0. log is always equal to the exponent, so 4 to the 0 equals x. So 4 to the 0 is just 1. So we can make sure that this log base 3 is happy by keeping x greater than 1. Because that means we're always in the positive part of the log base 4, so we're always plugging a positive number into the log base 3. Now, going out one more layer, corrupt converter is calling x greater than 4 to the 3. Who knows the strength of the homework? I'm being told because of how being opponent trying to do is impossible. Oh, really, corrupt? I'm not sure where the 4 to the 3 is coming from. So now what's happening? We need to assure ourselves I wonder if I'm not doing this in the best direction here, because now this feels like it's a bit of a pivot, but we need to make sure we're not plugging something bad into the log base 2 on the outside. So let's take the inside and make sure set it greater than 0. But I'm not sure if this is the right way to explain this, so actually, you know what? This might just be a better approach to the problem. Like, potentially we can ignore the approach that I was doing up here. Let's maybe follow this train of thought through. Sorry about that. Because maybe working from the outside and going inwards is a better idea. I think I see where your form is coming from, corrupt, or at least something like it. Because we have a really convenient manipulation we can do here, is we can do 3 to the power of each side in this inequality. 3 to the power of log base 3 cancels. And so you just end up with log base 4 of x is greater than 3 to the 0. And 3 to the 0 is just 1. Log base 4 of x is greater than 1. And now we can do the same exact thing to deal with this log base 4. So do 4 to the power of each side rather than 3, of course. So in theory, we're getting x is greater than 4. I don't know what that means, corrupt. X greater than 4 is correct? Oh, funny. Yeah, okay, so the approach I was doing at first, I think, is not good, or at least I don't see how to continue the approach I was doing. I would probably ignore that part that I was doing up there. Yeah, I would skip straight to this part. No worries. Thank you for the question. Okay. It'd be 5 to the 4. Yeah, I can see, like, as soon as you start adding on more logs, you start to get like a tower of exponents, or yeah. So it's funny, the first one's like that 3 could have been any base you wanted, and you still get the same answer. Funny enough. Okay, so critical. I'll type your name in chat in case you got up. Awesome. You say C and everything is yeah. Okay, so I need to remind myself on what Kirchhoff's rules are. Right. The current flow in needs to equal the current flow out. At any node. Yeah, sure. And then the voltage around any loop must be 0. I think you need to start. Oh, okay. I think your loop direction is wrong. I mean, from what I remember, you can define any loop direction you want. You just have to be consistent in the whether things have a positive or negative sign. So I would be inclined, at least for the top one, to make a loop like that, just kind of following the arrows that they provide. I mean, and then it's minus V? What is minus V? Because this battery is contributing positive voltage and this battery is contributing positive voltage because the direction agrees. If we down in this loop though, this battery is going to disagree and do negative voltage, I think. Hey, is it Irades? Welcome in. I remember seeing you pop up yesterday. Somehow you learned it differently. There are two different versions of how people think about this, using loops versus like nodes. Pre-node is positive, post-node is negative. You did the same loop direction as me? Okay. I mean, are you talking about like the current? So in the current is point plus sign, then it's plus V? You're gonna try the nodes too? Yeah, I mean, I haven't quite figured out which one critical is using. So when I work with the loops, at least critical, I don't think about you can use anything. Okay. You prefer a loop. Okay. So I just move around the loop in whatever direction I choose, and I add or subtract the voltages and make sure they're 0. So I'm going to just start with this battery here. It's contributing positive voltage because we're going from negative to positive in this loop direction. So that battery is contributing positive 18 volts. This resistor is dropping voltage. And we, since V equals IR, I think I think it should be I1. Times the resistance of 8 ohms. So I know how to determine the loop direction. You can choose any loop direction you want. But I'm going through the process right now to show how you, oops, I already wasn't consistent. You have to think about, given the direction you've chosen, how do you determine a voltage increase or decrease? That's the entire like task when you use loops. So if you're going along the direction of a battery, you're increasing voltage. A resistor is going to decrease your voltage. Yeah. This feels weird though. If I chose the other direction, wouldn't everything be negative by my logic? I might have said something slightly wrong there. I need to... I know for a fact you can choose whatever loop direction you want. And the thing you have to do is figure out what sign things have given that direction. Okay, that's how they do it. Right, $10, yeah. And that's the entire thing of like that's what happens if you reverse the loop, right? The question I'm running into in my head is that, like, in this example here, if you did reverse, okay, the resistors would be increasing your, okay, yeah. Okay. Ugh. So I'm gonna forget about the I1, I2, and I3 they give in the problem. My I1 is the current going around this loop here. And my I2 is gonna be the current going around this loop here on the bottom. Because they're I1, I2, I3, I don't know how to work with those directly. It just feels a little bit weird. Can we do the opposite direction? Yes. Do you want to do the opposite direction? Yeah, okay. I think this direction is easier, but they should both work. So in this case, I'll still start with this battery up here, just arbitrarily. I2 plus I3 equals I1. I think it should be I2 equals something with I think the relationship is, I don't know offhand. Hey Mega, to work with the structure, you just look at each junction, how much current is flowing each path using in fact total current junction. Oh, okay, when you say it like that, like right here, we would have I1 equals I2 plus I3. Because I1 is going in, I2 and I3 are coming out. So I guess you're right then, Barry. My bad. That's if we take the I1, I2, I3 from the problem. If we do I1 and I2 with these loops, which I should maybe find a different letter, but I don't know what letter to use, right? Or to use that's better. Junction and nodes are the same thing, yeah. Oh, we've just been calling them nodes. I think that's the typical term. Okay, but if you say you prefer the loop way anyway, so I'm going to use like the I1 and I2 that I've drawn with these loops. So starting with this battery, we're going against the flow of the battery. Like the battery flows from negative to positive in reality, but we're doing this clockwise thing. So we're going from positive to negative. That's against the grain. So it's going to be a negative 18 volts. And I think for the same reason, a resistor would normally drop your voltage, but because we're going against the direction of the battery, like this resistor is going to be positive. So it's going to be plus our loop current I1 times the resistance 5 ohms. Coming down around here, I think same thing with that resistor, 7 ohms. Still our loop current. What about 8? We can start with 8. It doesn't matter where we start. I just chose that battery because it looked nice, but we can. Like I can put the 8 in front here. It's gonna be the same thing. Like I1 times 8, it's gonna be positive. Well, there's only 2 loops and there's 3 like node currents, so I don't know how to do that, Barry. I'm not good with circuits, so I'm not saying it's not possible, but yes, critical. Oh, I just did something weird. The current is the variable that we're solving for. So like the current in a loop is always going to be the same. That's the kind of fact that we're relying on using this loop kind of method, which is like the current around this loop, we're just saying is I1. Like we're going to figure it out after this. So that's where things get weird, critical, where the problem has provided us I1, I2, and I3 involving nodes. But if we want to use loops instead, I think we need to make a completely different I1 and I2 for each of the 2 loops. I think. And then afterwards, we're going to figure out how to translate it back into the I1, I2, I3 the problem gives us. That was my thought with this problem. Yeah, it's something like that, critical. I looked at this node here, and I saw that there's I1 flowing in, and it has to be equal to the I2 flowing out plus the I3 flowing out. Oh, I made a mistake on the 7 ohm resistor piece. Loop current lowercase? Yeah. Okay, let's make the loop current lowercase. So I believe with when it comes to the 7 ohm resistor, it has I1 going that way, but it also has I2 going through it the other way. And I think we need to do I1 minus I2 times 7 ohms. So this 8 and 5 are definitely only I1. The 11 and 7, I think, are both I1 and I2. And then that 5 on the bottom is only I2. I think that's how this works. In this example problem, I'm looking at this simpler example where this R3 resistor has I1 going through it in one direction and I2 going through it in the other direction. And you see that reflected in the equation there. There we go. In that piece of the equation. The first loop requires 2 different currents to eliminate loop 2. Well, yeah, so I'm not done yet with the, sorry, in response to the 12 voltage, like, I'm not done writing this equation yet. I'm just slowing down to try to answer the questions that you're asking already. No, it's okay, Critical. I'm trying to make sure that I'm just like not moving too fast. And I only half know what I'm doing here in the first place, so I'm figuring it out as I go. So what we've done so far is we started at the 8 ohm resistor and we're traveling around the loop clockwise. And we just did the 7 ohm resistor. Yeah, so we still have to do the 12 battery and the 11 ohm resistor there. So because this battery is also going against the grain of how we defined loop 1, it's going to be a minus 12 volts. And then this 11 ohm resistor is going to have the same I1 minus I2 times its resistance. And we know the voltage around any loop has to be 0, so we said equal to 0. I'm being a little bit extra, including all the units and stuff here, but we're going to get rid of them. And all the point zeros. Let's just do that now, to be honest. 8I1 minus 18 plus 5I1 plus, I'm going to distribute that chunk there. 7I1 minus 7I2 minus 12. Going to distribute this chunk. 11I1 minus 11I2 equals 0. Group common terms. 8 plus 7. Oh, wait, no. 8 plus 5 is 13. Plus 7 is 20. Plus 11 is 31. I1. Negative 7 minus 11 is negative 18 I2. Negative 18 minus 12 is negative 30 equals 0. Okay, good. So we have one equation so far with two unknowns. Let's use the other loop to get the other equation with I1 and I2. Nope. I only solved one loop so far. When it comes to the second loop, where do you want to start, Critical? Sorry, I solved the entire first loop. We have not started on the second loop. Got answers that check out? Okay. Do you want to know the current too? The numbers come out nicely? Oh no. What do you mean by current too? Like, this right here is from loop 1. Yes, it's going to get counted again in loop 2. Yeah, I was trying out this playlist. It's not quite the right vibe, at least for this. Yeah, it's, you like it? Oh, good. Yeah, I mean, I haven't paying enough attention to it, but it came out recently. It was actually made by like a streamer working with a musician who made some music for a game I like. So we're multiplying it because we're getting the total current, I1 minus I2, times the resistance. That's the voltage, like V equals IR. It's just the current looks a little weird because it's I1 minus I2, but it's still current times resistance to give us voltage. So that's like the node way of doing things. That's why I'm using this lowercase I thing. Or that's what I think the node way of doing things is. Like, if you want to do it the loop way, we need to define our own i's. This lowercase I1 is completely different from the uppercase I1 the problem provides. We can translate back and forth between them, but they are completely different. Yeah, Mega. I mean, you're right. They're not completely different. I agree with that relationship you put there. Sorry, when I say that these two I1s are completely different, they are related, but we shouldn't mix them up because they're not the exact same. So if we proceed with the second loop with my lowercase I2 that I defined, I'll just start with a 5 ohm resistor here. And say that it's only being affected by my lowercase I2. So I2 times 5 ohms. Now we keep going around the loop. We encounter this 11 ohm resistor. So we're going to add it. And say this time we'll do I2 minus I1 because we're following loop 2. But we do have to account for I1 going the other way. And then we encounter this battery, which we're going with the direction of that one, aren't we? So that's going to add to our voltage. Plus 12 volts. Then we encountered that resistor there. Wait. How do we know which resistors are adding or subtracting here? This loop is a little bit harder because the batteries are facing the same way. Should one or both of these resistors have the opposite sign? Or should this resistor over here be negative and the other two are okay? The current through them does. Hmm. I'm getting confused on what's positive and what's negative in loop 2 here. The node way is probably actually easier for this piece, to be honest. Or at least I don't understand the loop piece. Or like the loop way. Yeah, I feel like this one is plus because it's kind of on the opposite end of that battery there. That's why. Should they just always? Hmm. Like, I'm getting confused on the 7 ohm resistor. Is that still plus? The thing that's giving me pause is that it's right. It's on the right end of the battery. Like, that's the thing that I don't know. No, yeah. I'd like to figure this way out. Critical with the loops because it was a lot easier for the first loop. It's just a little bit weird for the second loop. It is still plus. All right. I trust Finbox here. If we keep going around, we get to the wrong end of the battery, so that's going to be minus. And that completes the loop for that one. But the node away might not be easier overall critical, which is why I'm still doing this. For that little piece of it, the node way might have been easier, but I guess we can clean this up. I hope I set this up right. I saw it hard locked. Thank you though. 55 plus 55 is 110. Hope you're doing well, dude. Do you know what the answer should be critical? Not been here in a bit. I need to scream. That's fair. You don't know the answer? Okay. This is an equation for. Right, yeah. The loop has a nice advantage that you have less equations to deal with. Oh, this album just looped back around. Let me get a different. Let me just do that playlist. Yeah, no, it looks like Penbox solved it too. I was wondering if you had the actual like answer key too. It's fine if not though. We can compare my answer with Fembox. Minus 18 I1. We have 5 plus 11 is 16. Plus 7 is 23. Oh, 23 is an ugly number. 12 minus 36 is negative 24. Their fractions over 389 in lowest terms. Oh my god. Okay. So our two equations and two unknowns. That's our first one from loop 1. This is our second one from loop 2. Now we have to solve for I1 and I2. You got similar? Okay. Oh, that's terrible, dude. Dude, 31 and 23 are both prime numbers. This is, oh my god, dude. Okay. Well, I guess we can get slightly lower numbers if we eliminate I2, because 18 times 23 is a smaller number. What's 18 times 23? 414. So we have to multiply the top equation through by 23, the bottom equation through by 18. It's the, oh my gosh. Okay, I'm gonna bust out my default Windows calculator here. 31 times 23. That's 31 plus 20. 31 times 23. 713. What was 18 times 23? 414. Thirty times 23, 690. Okay, 18 squared. I feel like I should know that, but I don't. 324. Plus 414 I2, 24 times 18. $432. Now we're going to eliminate I2, so let's subtract them. Add them, sorry. Same thing, you know. 713 minus 324. I'm not doing that mentally. You got the opposite sign for my constants. Those are from the batteries. So I do have them like... Do you have your constants on this side of the equation also? Oh, it's because we have the opposite loop direction, right? Oh no, but you said they're not all multiplied through. Constants on the right hand side and they're negative. Okay. Keep going? Okay. 389. I won. That matches what you were saying. Because of loop direction? Okay. Hey, punching. That might be the wrong, like, chat, but hi. 690 plus 432. 1122. Taking discrete in Calc 3 next semester, I'm kind of scared. Calc 3, I think, is fun. Discrete math, I did not think was fun. But if you haven't already, you should become friends with Stookie. Especially. But I think Penn Center also enjoys some. And I'm sure Zach enjoys a bit too. No Zoom options online. Oh, it's only online. So like not even... Do you mean like you have to go in person, or you can only do like a purely online class with no lecture? So I assume 1122 over 389 is not reducible. It sure isn't. Okay. Okay, yeah, that kind of sucks. That it's only purely online. Yeah, we just... So this is for the loop, small I1 this is what I get. Hey, Jed. We use this to find the small I2. Being online such a blemish on the whole education system. Yeah, a purely online class. I took classes like that for general ed classes that I didn't care about, but they do feel like kind of a scam. I was afraid the activity is going to break up my stride. I tried to figure out if that's a reference to something, but I can't figure it out. Is 389, was that 23 times 18? Am I going to have an easier time by plugging into equation 2? No, it wasn't. Okay. I'm just going to plug it into... I'm going to take this I1, and I'm just going to plug it into equation 1. Yeah, critical. So we do 31 times 1122 over 389 minus 18i2 minus 30 equals 0, and solve that for i2. I'm going to break on my stride. I'm going to slow me down. Gotta keep on moving. So critical. That's why I'm using this weird lowercase I thing. I'm completely thrown out I1, I2, and I3 from the problem. I'm throwing those away until the very end. With the loop method, you only need the current loop, which I'm calling lowercase I1 and lowercase I2. So I3 is out of the picture. So is uppercase I1, I2 and uppercase I1. We can go back and translate how we need it. They're both the same accuracy. Sometimes one is easier to set up than the other, but they both lead to the same answer. I mean, usually loop is easier to set up, to be honest. I'm just not very good with circuits. 31 times 1122. Oh my God, I keep doing plus. 34,782. What a fantastic number that isn't. I'm gonna let Wolfram Apples solve the rest of this for me, I think. 34,782 over 389 minus 18x minus 30 equals 0. Survey says 1284 over 389. $12.84 over $3.89. You're like, yeah, I was doing it by hand. Usually I jump straight to the calculator. 89.41? I don't know. Let's find out. Dude, Wolfram Alpha isn't giving me the decimal. Come on. I guess I'm doing it in my Windows calculator. No, that's 3.3. Oh, I could have told you that. Or not, I couldn't tell you that exactly. I could have told you it was about 3. The other fraction is going to be like 3.2 or something really close. Okay, so what we found is that the loop current is 1122 over 389. for the first one. The second one is 1284 over 389. What number was 1122 at 389? $12.84 over $3.89. Okay. So now we can go from the loop current to the I1, I2, I3 that the problem provides. Should I have gotten a negative sign for my small I1? No? Do we add a negative sign? Because I feel like the small I1 and the big I1 are opposing each other. But I feel like the current is rightfully flowing with big I1. Or are we do we not care about the direction? Are we only doing the magnitude? I don't know. Capital I1 is pointing the wrong way. Really? They drew it the wrong way? The current is actually flowing the other way? So if I say that capital I1 equals negative 1122 over 389, it should be like that. Okay. Huh. I didn't expect that. I guess you do have the battery going the other direction in the middle. So yeah, that's what we're doing right now, critical. The way we do that is, and sorry, I wasn't explaining. I was trying to figure out for myself first. Node voltage checks out. Okay. Thank you for doing it two different ways, $10. So critical. The way we translate from loop current to the node currents or branch currents that the problem actually gives us is the current around the entire loop in the direction we found is this 1122 over 389 number. The current around capital I1 is only influenced by that loop current. There's nothing else interfering with it. And we'll see what that looks like when finding I2. Wait. The loop is not the voltage. No, you can caps lock, I don't care. I thought you were excited. The loop is not the voltage. No, this loop, this entire... We use the loop, we use voltage to solve for current. The voltage around the loop is 0, and we use that fact to find the current. So the loop is the current. It's kind of the same thing, to be honest. It's both the current and the voltage, I guess. Around the same loop, we look at both the voltage and the current. We're using we know more about the voltage, so we use that to solve for the current, I guess. And so this capital I1 up here is only influenced by the loop one. Like there's no other loop attached to it influencing it. The only thing that is weird here is that the loop we defined has the opposite direction to the I1 they define. So it would be that small I1 equals big I2, but because we define them with opposite directions, we have to take the number that we got and insert a negative sign. So capital I1 is negative 1122 over 389. That's the number we got for small I1 for that loop 1 current. And so I hope that's okay with you so far. It depends what you mean by always. Not always multiply by negative 1. You only multiply by negative 1 depending on the direction. Here, the direction of the loop disagrees with the direction of the current they defined. That's why we need the negative sign. Otherwise, we don't include a negative sign. Cartesian axis? I don't know what that means in this context. So I mean, no. Oh, I get what you're saying now. It's nothing like that. No. Just because I1 is going left there does not mean negative. The reason there's a negative is because our loop is going clockwise that we defined, but the I1 they have up there wants to go counterclockwise. They have different directions. That's why. It's because they disagree on the direction piece that we need a negative sign. And so maybe seeing how we think about I2 is going to help reinforce this. So the capital I2 is defined to go to the right. So capital I2, well, it's affected by both the small I1 and the small I2 loop currents. It's going to involve both values. Now, small I1 we define to be going that way around the loop. So that's another case of opposite directions. So it's going to be a negative small I1, but I2 is going the same direction. So we're going to do plus small I2. Because there they do agree. And then we can plug in the numbers that we got. What is that? 162? So big I2 is the sum of our loop currents, but we have to think about sign. Positive or negative. Oh yeah, usually Fembox, I either sign into my Discord account on my phone if I'm getting off my phone and post it directly from it, or I literally email the picture to myself and post it, like, and download it on my PC. Yes. So, this is the answer for going from our loop currents to the capital I2 they define in the problem. And so there's one more thing. We have to get I3 now. I3 is going to the right, but we defined our loop current the opposite way, going to the left. So we need another negative sign. So I3 is going to be minus I3. So minus 1284 over 389. And so that's why when I first saw this problem, I wanted to do the loops the other way. Okay, I'll repeat it. So, oh, I wrote down the thing wrong. I2. So capital I3 is going to the right, but we defined our small I2 loop current as going to the left there, because that's the clockwise direction. So that's another case where the directions don't match. So we need a negative sign. So capital I3 is equal to small negative I2. Negative small I2. Yeah, thank you, Raven. How do you know that? The negative sign, or, oh, that I2 is not, because that's how we defined I2. So we defined I2 going clockwise. So on this bottom wire, it goes left. On this wire on the side, it goes up. On the wire on top, it goes right. The wire on the bottom, it goes down. That's our loop small I2. But then they gave him the problem, I3 goes right. And that's what causes the issue. Sure, yeah. And so at the beginning of the problem, I wanted to define the loops the other way, going counterclockwise, because of that exact reason. It would have made the directions agree with each other and we wouldn't have needed the minus signs. But we can also validly choose to go clockwise and just be careful about our minus signs. But it would have been more direct, or, we wouldn't have had to worry about this as much if we chose our loops going the other way. Yeah, only the second row has both loop currents involved. Yeah, if you're ignoring the signs in what you just put, sure. The I2 involves both because it touches both loops. I1 only touches one loop. I3 only touches one loop. But since I2 touches both loops, it has to involve both loop currents. Okay. Let me see if I can figure out how does this. Um, when it comes to the method, yes, you can choose whichever direction you want. So if I was doing this on my own, I would have chosen the other direction, but you can choose either one. So I would have chosen the other one. I already made it a PDF. It should be okay. Thank you, though, Raven. Let me check the PDF, actually. Okay, it came out readable. So it's a matter of preference. You can do it either way. I preferred defining the loops the other way because it agreed more with the currents they defined in the problem. We wouldn't have had to worry about the minus signs. And I just liked how it followed the flow of these batteries. So I guess those are the two reasons. Yeah, and also the batteries are probably the bigger thing for me. I like to follow the batteries from negative to positive if I can. I didn't really think about I2 at all. Okay, well, I guess, yeah, I chose it more based off these like batteries on the edges, just trying to agree with them and go in the direction they want to go. But there is the added bonus that it also agrees with the I1 and I3 the problem provides. Okay, I did just put the PDF in that Discord thread. And it only ignored I2 because it's in the middle and it's a little bit harder to figure out. Like when it's touching both loops, it's a little bit it's weird. So I just looked more at the edges that only touched one loop. For the purpose of looking at direction, yeah. Another thing too is that once you choose one direction, you usually want to choose the same direction everywhere else too. But that tends to make it a little bit. If you keep on switching the direction in the same problem, it could be easy to get mixed up. You can do it though. It's just a little bit easier if they're all clockwise or all counterclockwise. All right, sounds good. God, that really tested my circuit knowledge. I did. It's in that Discord thread. It looks small. Well, I have a bunch of other junk in this PDF. Oh, it's Apple's stupid proprietary image format. Um, all right, I'll post this. Try this other version of the PDF and just scroll all the way to the bottom. How do I kill it? Dude, HEIC files are just stupid. I've had the exact same issue and I couldn't figure out a way to convert it to normal file format. Because Apple just can't be on the standard, I guess. Convert HEIC file. There's this random website here that'll do it. Let me try it with what you posted. Uh, I can tell you where it is. Critical, 1 second. Okay, this website seems to have converted your file, Fenbox. Okay, just give me a second and I'll, Okay, so first off, I'm going to post Fenbox's work as well. In there. And then if you want the book, so I'm using like an entire textbook. If you want it, go to the reading group channel, look in the pins, and that's the PDF for the textbook right there. It's a big file though, because it's an entire textbook. And the page number, and the textbook is really advanced. It'd be, you might understand that chapter, but they use a lot of multivariable calculus and stuff, and it's not the best to learn from necessarily. But the page that I was looking at is page 212 from my textbook, and I'm putting that in the Discord channel too. If you want to like have that to refer back to. But the textbook in general is really out there. It's a very difficult book. So if you don't get it, I would just look for a different resource, to be honest. But that problem you probably would understand, so you could still try it. It does show it both. So on page 212, it does show both. It does the same problem with nodes. That's the first solution. And then it does it again, but with loops. That's the second one. So I bet that like section 4.7 here, it should be fine for you. I don't think they go too crazy with the calculus. or 4.10 rather. And if you want to go more, they do have some practice problems with that in the problem section, along with solutions. So just look for a figure involving a circuit. So like figure 4.37, like you could do number 12 there, or something, and then look at the solution in the back of the book, and they explain it in great detail. Okay. Okay. How long have I been streaming for? 4 hours? Yeah, no worries, Fenbox. I've had that exact same frustration. It's really annoying. We'll do a couple problems, then we'll probably wrap things up. So like, I just want to celebrate getting through all the Atwood's machine problems. Now I can suffer with a new type of problem. This is much better, right? Oh god, there's still a pulley in this figure. I shouldn't get that excited. Ugh, just can't escape them. No worries, critical. Morton loves his pulleys. Oh no. What? There is no friction. Oh my god. What is even happening here? All right, well, I would probably need some free body diagrams. Um, so M1, I think the only thing we're really interested in is being pulled to the right by tension. Sure, it's being affected by gravity, but that's being balanced out. Like, that's just gonna be, the normal force is gonna take care of that for us. So I think M1, we only need to worry about tension. M2, we have the same tension going up. It's being pushed to the right by the big block, and it's being pulled down by gravity. So if the big block doesn't move at all, then mass 2 just falls straight down to the ground. Um, I might be drawing this from the wrong perspective as well. What is the big block accelerating to the right doing? Like, it's making the ground underneath M1 like slip away, but I don't think that's what I'm supposed to think about, unless I don't feel like. Yeah, the tension is going to be uniform because the string is massless. Equal to G. It's not gonna be equal to G. It's gonna be equal to like some mass times G, and maybe there's a fraction involved. Well, okay, so if we're saying there's no relative motion, I think we do know from the free body diagram on the right, T has to equal M2G. That's gotta be true. And maybe I think the perspective we might want is for us standing on top of M1. Because rather than M2 being pushed to the right, it's going to be more like the world is moving to the left below us. Can we say that? In which case, MA also equals T? This feels too simple though, right? M1 is irrelevant? Is that okay? Saying that MA equals T doesn't feel quite right to me. Oh, am I thinking about Newton's third law wrong? Is M2 pushing back with force MA, but then also going to the right with the normal force? I never get how that works. I keep forgetting. But I don't know how the left and right forces on M2 even make a difference, though. The tension is only going up in M2's world, and gravity going down. Left and right forces, I don't know how they make a difference. Or should I not have an arrow to the left at all? Oh, okay, that's how I'm... Only include normal force to the right acting on M2, not the force left. Okay. And there's no way that MA coming out of the left side of M1 is right. It's just... I would rather think about this as the acceleration of M1 due to the tension has to be balanced by the acceleration of the block below it. So I'd rather write M1A just equals T. Maybe A1. As you meant initially? Okay. Do I want this to be A1 or just A? I think A1 should be equal to A, maybe opposite in magnitude. Oh, hey, it's the song. It's a good song. So we're gonna say M1A is equal to M2G? Hey, man, just a banger. Hey, Lycan Dragon? I'm sorry if I'm saying that wrong. There we go. Thank you for the follow. Welcome in. How's it going? Does M1 does have G, but I don't think it's important. I mean, so now the big M has dropped out. That feels like it's okay though. I don't know. Oh, does TikTok use the song a lot, Sereno? Also, hey. I wouldn't know. Like I don't go on TikTok, but so I don't know, does this check out? If M2 is huge, the acceleration should also have to be huge, right? If M1 is huge, then M2 is hardly pulling on it and you don't need very much acceleration at all. So that's okay. The units check out? This might be my answer. I'm gonna keep saying things in this high-pitched inflection. The big M dropping out, I think I'm okay with. It doesn't feel like it should be all that relevant. All right. Number 14. Let's see. I did something right for once. Okay. Hell yeah. I'll take it. It was the song, you're right. So yeah, like, and if you have a question, feel free to let me know. These physics problems are just kind of things I've been doing because I find them interesting in the downtime while I don't have a problem from chat, basically. Just play them on repeat and get a physics PhD in no time. True. I I have to explain to the committee why I'm wearing headphones during my during my defense. Like, all right, see you, Zumetto. Thanks for being here. It's a good song too. It's not like as much of a banger as that song, the last song was though. Yeah. Be back in a sec? Sounds good. Come on. Okay. Block with mass m sits on top of a block with mass 2m, which sits on a table. The coefficient frictions, both static and kinetic, between all surfaces are mu s equals mu k equals 1. Okay. A string is connected to each mass and wraps halfway around a pulley. Wait. That is not halfway. Are you telling me this is half and half? Pulling the pulley with a force of 6 mg. So the bottom block must slip with respect to the table. Assume it doesn't slip and show this leads to a contradiction. So the top block must slip with respect to the bottom block. Same hint. What is the acceleration of your hand? Well, let's look up, like, how does friction work again? These pulleys have all been frictionless. Oh, half the pulley. Okay, that's fair enough. I'd much prefer to think that I'm just smarter than Morin in that he wrote a crappy book and I could write a better one, okay? um, how am I learning from a PDF? I can't learn like that. You just kind of stick with it. I feel like there's some things that I'm not understanding and just kind of moving past, but it turns out there's people out there who are really good at writing textbooks, so. If there is slipping between two objects. Wait. Maybe I don't know what slipping means. I thought slipping kind of breaks friction. No. Yeah. What? If there is no slipping. Too many words, I'm too lazy. I like more symbols / pics. I feel like you just need to get off TikTok. God, I'm sorry, but my nose is running. I'm gonna be back in a minute. Okay. Yeah, I mean, I never been on TikToks. I know it's just like too addicting. I can't judge though because I do other stuff that's not good for my brain. But Emily's good about like not downloading TikTok or Instagram or the stuff that really tries to suck you in like that. Never used. Oh, I assume that you weren't TikTok because you talked about it before. It's not even taking me. It's dumb. Yeah, I mean, Vine before I thought was the most stupid thing I've seen in my life. I still think that. And so that gave me an even more negative opinion of TikTok that replaced it. Okay, or Twitch. Are you saying that Twitch is like also addicting but dumb, or like what do you mean? Or like Twitch is also brain rot? For some things, I completely agree. I hope this isn't brain rot. um, it can, yeah, it can be. Okay, I think we need to figure out some normal forces here. Um, oh, so the 2M block is also being weighed on by the M block above it, right? So is this actually going to be 3 mg? And minimize the pages and zoom in. I guess I don't need that pane, do I? Does that help? Why is this such a hard question? Is this 3 mg or 2 mg? Let me just go with 2 mg. Which means the table will be pushing back up on it with an equal normal force. I feel like it's 3 mg. The table's holding the weight of both. It has to be pushing up with the same amount, right? The small block is just being pulled down with mg. There are two objects touching that block, so there are two normal forces on it. Oh no. That's how I should be thinking about this? Why is this stuff harder than math? I don't know. I wish it was easier. Okay, we definitely have a gravity down 2 mg. Now, both normal forces. So they basically fit. There you go. E&M, for what it's worth, is super fun. Mechanics so far, I really don't like. But I want to learn it so I can learn relativity. So I hope it's going to be worth it. I think it will. Is it easier to start with the top block? It has a downwards force from gravity and an upward force from the normal force of the bottom block. Differential, oh. I mean, I assume you need a basic understanding of mechanics here. So I'm going to assume the table is doing a normal force to counteract the weight that's on it. Is there another downward force that's normal because of the small mass? Yes, okay. I'm not even gonna go to the left or right forces for now. Am I missing anything? There's a third law pair between those two free body diagrams. Right. These two. No. No. Those are not equal and opposite. They're equal and the same. These are equal and opposite. And I mean, are you saying it's between the two, like crossing over? I feel like like all of these forces add to zero, and all of these forces add to zero. But I don't know if a dotted line or like of a box to draw that goes like between the diagrams like that or something. It wouldn't be those, but two forces are exactly the same force, just acting in two different directions. I don't see it. I keep wanting to relate these two forces because it's the same thing with a different name. Like just like the gravity force being passed through, but it's not that. Um no, I have no clue what's the same force here. These feel like different forces. that are caused by, or some are caused by each other, I guess. Well, I was confused because they're not. Well, I don't know. I circled a couple things, but like, I want to relate these two things, but they're going the same direction. Like, oh, wait, is it these two normal forces? Oh, they're pushing back on each other with the same force. Okay. So, like, we could write that. Okay. So, I guess now when you think about the pulley, tension, tension, 6 mg. So each of these tensions are half of 6 mg. So we have a tension force going to the right at 3 mg, to the right at 3 mg, and then either a static friction or a kinetic friction. I think that's the question. Well, they're saying it must slip, and the chapter was saying that slipping is kinetic friction. Must be that the static friction equals to, well, should do a 1 and a 2 maybe, or I guess 2m and m. Um, So is this the sum of the normal forces the block is experiencing? What exactly is the normal force that the book is It's the friction between the 2M, where we're starting with the friction between the 2M block and the table. So it should only depend on the normal force the table exerts on the 2M block. I hope. So this is going to be Fn table. And we know that mu s is 1. So Fn table. And this has to be... You can solve all the y equations before worrying about the x motion. Oh, too late. That's probably worth doing. How do I get my... Probably in view. Pair pages? What the hell? I don't know what that means. Sidebar. What? Ugh. You know what? I already posted the PDF for critical. I don't need this anymore. There we go. Much easier. Okay. Maybe I should do some... Okay, so... Oh, let me... There we go. I guess you're right. I probably should work out Fn table is equal to 2mg plus Fnm, right? We need negatives, right? We know this right here. And we also know Fn2m is equal to minus mg. So then from the two equations on the right, I think we know that Fnm is equal to mg. And that tracks. That makes sense. I hope I'm doing these signs right. Table equals 3mg. So I do think the normal force table should be 3mg, so that seems like it tracks. Why is down positive and up negative though? Because I put the negatives in the wrong spot. Because I was being lazy. I feel like, I don't know. Will that really fix it? I don't need negatives in any of them? Yeah, okay, you're right. I already know what the directions are. Maybe I should only worry about the magnitudes. Wait, that's not a contradiction. Um, I thought the contradiction was going to be that the friction force is going to be less than the force of my hand with the pulley. I'm getting that they're equal, though. They're... Oh, okay, I guess we should investigate the other one. Oh, wait. The normal force? What normal force do I want? We want the friction the M block is experiencing. And the M block experiences a normal force from the 2M block. And the 2M block is mg. It's also be that FSM is less than or equal to wait. 3mg needs to be less than the static force. Static friction. Tension equals 3mg. So less than or equal to F sub s, which equals mg. This is a sloppy way of saying that. I think I'm doing this backwards. Oh, yeah, I am. Or I'm not doing it quite right. This should be an inequality. This also be, the tension should be equal to the static force since there is no slipping. But mg is not equal to 3mg. Therefore, the M block must be slipping. Wait, I did part B. The bottom block must slip with respect to the table. The top block must slip with respect to the table. I thought that checks out. We don't have the same contradiction. Two friction forces. Oh. I thought when it said with respect to the table, I guess that means positionally. I thought I meant only consider the table, I guess. So that's what you meant with the two slipping surfaces, I guess. I interpreted oh no. Undo. This is there is some jank with this tablet business, but it is really nice to be able to rearrange text like this. You definitely can't do this on paper. All right, that'll all be part B. What is this thing? It must have been from the line above it. Oh, it's the A from the table. Okay. So that means it's 3mg plus mg equals 4mg. Okay, now we get a contradiction. Okay, that's answer part A. Part B. I'm not gonna bother rephrasing this. That's my answer for part B. The make-believe professor can dock me points if they don't like that. What is the acceleration of my hand? Okay, so to get the acceleration of my hand, it's m, the mass of... Does my hand have mass m? I assume it does. We're gonna do good old 6mg to the right, and then we have two tension forces to the left, but tension... Ooh, we need to figure out what the tension is. Tension is equal to the kinetic... I assume we're going to sum up the kinetic frictions and set it equal to 2 tension. Well, or is it the friction of the top block equals tension and simultaneously the friction of the bottom block equals tension, and hopefully those agree with each other? We know they don't agree with each other. One is 4mg, one is mg. I think in total, I think we sum everything up. I think we say 2 tensions equals mg plus 3mg. So T equals 1/2 mg. Oops. 2 mg. No. No. I'm phrasing this terribly. um. The kinetic friction of the 2M block is equal to 4 mg by the work I did last time. The force of kinetic friction on the bottom block is just mg. Something's not right. Or I don't. Okay, I'm gonna be so because there is supposed to be a net acceleration now. Maybe the easiest thing to do is to draw this free body diagram and say there's 2 frictions going to the left and a 6 mg force going to the right. And the frictions sum up to 5 mg. The force to the right is 6 mg. So then MA is equal to 6 mg minus 5 mg. So A equals G. It's my answer, and I'm sticking to it, maybe. Unless I see a flaw in the time it takes me to check the solution. Yeah. A equals G. Oh. That F1 right there is concerning. Welcome back, Lycan. I might need to account for that. Really? I guess it's an equal and opposite for like thing. Oh. You know, it kind of makes sense if the expression in my hand. So I haven't seen the answer for part C yet, but I think I'm going to revise the answer that I put because why did oh I get why this window gets reset sometimes. It's because I'm hitting random buttons on my tablet while I'm clicking into OBS while not realizing it. That's annoying. Hey, Edison. So the thing that I missed is that there's another force coming out to the right on FK. Not that. M. It's because this friction force has an equal and opposite friction force on the other block, I think. And that kind of makes sense. Like, it doesn't. The more I think about it, the more. Like, the friction between the two blocks shouldn't matter for the entire system, I feel like. I hope. So. Or at least it cancels. Let's rewrite this. F equals ma equation for my hand. So to the right, 6mg. To the right again, the equal and opposite friction. Was I calling that just m? Yeah. But there's also a left force of the same thing. So those two things cancel. So it's just going to be 2mg. So A equals 2g is my new answer. Right? Because that's 4mg? Yeah. This kind of perfect contradiction feels a little bit weird. Like, I feel like you don't really need to make it a contradiction. You could just analyze the situation and say there's more force on the block than static friction could overcome. Whoa, that's a weird argument. What the hell? I did be completely wrong then. Uh, if it's possible to type out there in chat, you can do that. If it's not, or if you prefer, I have a Discord server as well. Those are the two like main ways. But yeah, I'm almost done with this, so feel free to let your question rip. Hmm. Weird. I didn't think of this at all. Hmm. Oh, they have different accelerations. Oh, because they're slipping. I hate this. Uh, just please forget about the police. I hate police. Uh, all right. So, like, I want to wrap things up soon. If you can get your question in here relatively soon, I'll look at it. But I'm getting tired here. I want to end the stream and eat some dinner soon. Yeah. Does 16 involve pulleys? Okay, at least 16 doesn't involve pulleys. Inclined planes, which... Okay, I think after this one, it seems like... Oh, God. We're forgetting about pulleys, at least. What's happening with 16? Let's at least read it. A block with mass M rests on a wedge with mass M and angle theta. Lies on the table. All surfaces are frictionless. The block is constrained to move vertically by means of a wall on its left side. What? Okay, let's look at your question. I'm coding a widget for my phone that's a date and time. I'm adding a button there that takes the current date, converts it into the date from a fictional calendar system. Given that this system is a lunar calendar where each month starts on a full moon, the new year starts on the first full moon after the spring equinox, the standard expression to convert the year progress between the two systems with a view to calculating the exact date. Ooh. Do, doesn't isn't the length of a lunar year just isn't it not always the same offset or something weird like that? I don't don't know exactly how a lunar calendar works. That's not what I want. Is a lunar calendar always this like a constant length? For some reason, I thought that it like the length of a lunar year could change. Hmm. Rounding here. Hmm. Oh. Hmm. Okay, that seems to say there's a constant offset. I don't know. How does that work though? Dredge? Yeah, I played that through. It's pretty cool. I played it on stream. I the VODs are long deleted, but it's cool. Hmm. Yeah, I'm sorry, like, and I don't even know how to start this. Like, I don't know. I need to find someone else to answer because I don't completely know even know how lunar calendar works, to be honest, in the first place. Oh, nice. Oh, that reminds me about Overcooked. Um, yeah, that Little Christmas that's a little bit short for how expensive it is. But if you're getting it for free anyway, then that's perfect. It's a neat game. Discord tomorrow is a starting point. Yeah. Hmm. Yeah, like if I could see the specifics, then maybe I can wrap my head around it better. But um, something like a fence post error. I don't know. Okay. Yeah, sorry, at least I don't immediately have an idea for you, so I'm sorry about that. Um, all right, sounds good. I think from here we'll oh, sorry, Jed. I'm like literally about to call the stream right now. I'm tired and hungry. I hope that the movie night was good though. Um. Ugh. Okay, so yeah, for anyone who's new around here, I'll just do a general shout out to the math streamers. Not the only one who does this. It's up to day 4. No plans to right now. I feel like Advent of Code is getting the problems really escalate quick. So if we did another coding competition, I probably want a different source of problems. Or maybe we only do 2 problems or 2 days or something. Oh, yeah, sure. I mean, if you want to talk about it now, I can take a few minutes, but I'm happy to talk off stream too. Take a kitchen break. I'm just not. It's usually it never crosses my mind until suddenly it does, and that's all I can think about, like food and bathroom and stuff. Um, it's just I don't know. Streaming just is too much fun. It preoccupies me. Off stream is fine. Okay. So I'm gonna cut the YouTube stream off here. So if you're on YouTube, thank you. Goodbye, YouTube.